Okay.
Hi, Chris. Have a seat. It hasn't started. Okay. A few TV news for a guy called James, who's over in the US but not in Dayton. So he's also.
If you go to the MIDCA-arts.org, it's on that. There's a link in there.
Oh, there's no one we've met, but it's someone who's taken part.
So is that video conferencing or what is it?
We're connecting somehow via Google Hangouts, but it's going to a YouTube stream.
Okay.
So we are just watching them. They are not watching us.
They can see us, but we'll mute that once the show gets on the road.
All right. So hopefully you all can hear me, and it's 4:02. So we're gonna go ahead and get started. This is live on YouTube. So we're doing a Google Hangouts. So it's a little different technical setup from last year. So just bear with us. We have some remote speakers that are joining us. We're really excited, and so I'm gonna go ahead and get started. So my name's Dustin Dannenhauer, and so I'm happy to host with everyone else the second annual MIDCA workshop. So this is coming to you from the Collaboration and Cognition Lab at Wright State University. And I just want to thank the sponsors who have funded MIDCA research over the years: NSF, ONR, Army Research, and the Air Force. And I've had a lot of people from different universities contribute over the years, from Wright State, Maryland, Lehigh, and Union College. So what I'm doing now is I'm just going to give an introduction, and then we'll get started. So I wanted to just talk about the objectives from last time. So last year, almost exactly a year ago, we had the first annual MIDCA workshop. The objectives we had. So one of the things we wanted to do is to create resources, which was pretty great. So we now have about 8 to 10 videos of the talks that we had last year, and we're going to have the same thing from the talks from this time. To build community. So a few different people have started using MIDCA for different research projects, and we wanted to bring them together and have a chance where we could all discuss the project. The other thing from last time is we got a new user perspective. So for new people, we had a demo of someone using MIDCA for the very first time and how that process was. And it was also just the kickoff. So objectives for this workshop is largely similar. So we want to. Oh, I'm going to mute. Just give me 1 second here.
Oh, there we go. I can hear you now.
Great. I'm just going to mute you, James, if that's okay. Sorry about that. Still getting used to the Google Hangouts. So so that was James Boggs. He's going to be one of our remote speakers coming from Union College in New York. And he's going to be talking about rebel agents. Should be an exciting talk. And we have Martin and Ryan joining us from DSTG Australia in Adelaide. It's Friday morning there for them. And Ryan will be giving a talk a little later. So over the last year, some of these new people have joined us, and so we wanted to welcome them and be able to have a conversation, have a workshop, and share new research results. And the other thing about this workshop is MIDCA has gotten a little bit more traction. So the theme of this workshop is kind of how does MIDCA shape up in the whole realm of cognitive architectures and AI, and what are we thinking about for the future? Talk a little bit about that. So the schedule is the following. So we have the first session. So we're in the introduction right now. After this, Mike will give a talk on cognitive architectures in MIDCA. And then we'll hear from Shravya, followed by James. And then I will give a talk. And then we'll have a 20-minute coffee break. So part of that coffee break is a little bit of a buffer of time in case a few talks run over or if we have any questions. So if you're watching us live on YouTube, please feel free to type any questions you have. We see those in the chat. Know that there is some delay. So it might take a minute or two for us to get back to you. And that's one reason, another why we have a nice long 20-minute coffee break. In the second session, we're going to hear from Ryan, followed by Venkat, Sampath, and Zora. And then we're going to have a discussion. So this was something we had last time. We had a long, like 45 to 50-minute discussion at the end. And that is a great time. So if you don't get to ask a question, or you're kind of wondering about something, or you have some comment, something you think is interesting, save it, write it down, and bring it up during the discussion. So during the discussion, we'll have a chance for everybody to talk about that. And then we'll have the closing. So, and we hope to end by 8 p.m. So for those of you who might be new, what is MIDCA? So MIDCA is, it stands for the following: Metacognitive Integrated Dual Cycle Architecture, designed from the beginning for metacognition. So this is an architecture for designing artificial intelligence agents to interact in a world. The dual cycles refer to cognition and metacognition, and they're integrated. They share a memory, and there is an architectural model, a formalism that's been described in a number of research papers, and we have a running implementation. So we have Python, mostly Python software, that has implemented MIDCA so far. So I'm just going to go through the cognitive layer briefly. Essentially, there are these 6 phases. So the agent perceives the world. You see here on the bottom right, which is part of comprehension. So it perceives the world. It interprets the world. It might note something unusual. It might generate a new goal it would like to pursue or consider pursuing. And then it evaluates its progress on its goals. Solving side, intend is where the agent decides what goal it should pursue, if any. And then the agent, once it knows what goals it's going to pursue, it'll generate an action or a sequence of actions to execute in the world to achieve that goal. And so this cycle continues, and these phases work with a shared memory. The thing about cognition is that this is dealing with the world. So it's perceiving the world, it's interpreting, what's unusual around me in my environment. Are there obstacles? Things like that. The metacognitive layer, which, as you may note, it looks similar in structure to the cognitive layer, is instead of dealing with the world, it's dealing with cognition. So if you notice, perceive becomes monitor, and act becomes controller. So it's now monitoring the cognitive layer, and it's interpreting if something unexpected is happening at the cognitive level. And so we see similar cycles here with intention and planning and controlling, where we might modify something at the cognitive level. So that's kind of an overview of the formalism. What's new for MIDCA over the last year? So if you look at our GitHub repository, we have about 100 to 150 commits. A good chunk of those are for the website, a lot of small edits for the website, which we have at midca-arch.org. So feel free to go there. A webpage for this workshop is up there. We've also moved repository locations. So please note that the new MIDCA repository is at colab2/MIDCA. And another thing here, the second bullet point, Python setup.py develop. For anyone who's developed MIDCA, there was this tedious interaction where anytime you change the code, you had to run Python setup.py install. And that's been fixed now. So to run MIDCA, you just have to do setup.py develop, and then any edits you made are already reflected when you execute it. Meta Aqua, which is in itself a whole research project, has been added. It does explanation among some other things, and more documentation on that is coming soon. And there have been a number of publications. So over the last year, these are some of the publications that have come out. The other thing I want to mention is, for those on the live stream, you can rewind if you need to. So if you feel I went too fast over a slide, or you want to know some details, feel free to just pause the stream at whatever slide you want to look at. So I'm not going to go into more detail about these. And so another thing is MIDCA's website. So we have, so this is great. This is a nice addition. It's using GitHub Pages, and this is kind of a shameless plug. Please, everyone, contribute to the website. So the website is just in the repository, right where MIDCA's code is. you'll see a folder MIDCA. There's a folder called docs. And so underneath docs, index.md, that's the homepage. So for example, it's kind of bare right now. So feel free to, we could really use a page with all the publications on MIDCA. So if you want to add that, it should be easy, and it's right there. So, and then finally, this is my last slide of the introduction. I just want to say, one thing we want to do is we want to make development on MIDCA easy. So if you want to run MIDCA for the first time, this is all you have to do. Clone the repository from GitHub, run this python setup.py develop. You will need Python 2.7, cd into the folder, and then you can run an example. And my personal recommendation that I've started using this year is PyCharm for a Python editor, which is great, and it's because MIDCA has a lot of different files. So that's the introduction. I'm going to wrap up, and we're going to go ahead and get started with our next speaker, which is Mike Cox, and he's going to be talking about in MIDCA. So just bear with me a minute while I switch over to his talk. And I'm going to pass off the headset to him.
Thanks, Dustin. That was great and very wonderful. I wanted to add one other thing. Yeah, thanks. One other thing to the new additions. Let's see that. Oh, now I just spaced it out too. I should. Well, I'll come back to that as I remember it. Hopefully, Dustin had actually asked me late last year to talk a little bit about MIDCA and cognitive architectures and put it into context. There are a number of other cognitive architectures that have been in existence for over 30 years. A couple of them, SOAR and ACTAR in particular, go way back, and they're very mature and sophisticated. And I think we see some of that, and we call ours a cognitive architecture as well, but it shares a lot with it. But I want to try to highlight a little of the similarities and some of the differences with that. So I think one of the ways to think about cognitive architecture is to also consider other kinds of architectures. For instance, just a computer architecture, or even just an architecture of a building. We have a blueprint. Blueprints determine where rooms are, what the layout of a building would be, what its external structure is to the environment, but not things like where furniture goes for the most part. A lot of details then are populated by the owner of a house after it would be constructed. But the architecture defines the important structural things and functional aspects and the aesthetics for an overall design. Similarly, in computer architectures, we have a fixed set of characteristics. I do want to say that this is taken from the old Intel 8080. I think that was the original IBM PC was using that. So this is extremely old. Some architectures think of it a little bit differently now, but for instance, pipeline architectures. But here we can think of an architecture as containing functional components, and the 8080 shows a few of those. And then the data paths, how they're connected, which one provides data for others, and a representation for the data, and an instruction set to perform computation and changes. Then the user on an implemented chip or system that has come out of this architecture, a person would then be able to model something in the world and using a program or a language that then gets mapped to that instruction set and run under that architecture. So cognitive architectures are similar. They provide a fixed set of functional units, the connections, and often a representation in a language. We'll talk a little bit more about that and how some people have specifically described that. Excuse me. So there's also a number of other related concepts that we hear too. We hear not only cognitive architecture, but cognitive systems. And in fact, there's a conference that we published in a number of times called Advances in Cognitive Systems. They have a journal as well as a conference each year. I think the current one's coming up at Stanford, and it is the 6th annual advances in cognitive systems. So what's the difference, between a cognitive system, cognitive architecture, information processing system, a cognitive agent, a goal-driven agent, or autonomy, reasoning? These are all related. So I will not focus on all of these, but some, particularly cognitive systems, it's a little broader. Pat Langley actually published in 2012 a really interesting paper. If you haven't seen it, you should read it. It's on the web and it's publicly available. He has defined 6 fundamental assumptions for cognitive systems that distinguish it from other AI systems. We go to AAAI and there are a minority of papers presented on cognitive architectures or systems. Not all cognitive systems model from a cognitive architecture point of view, but they do usually assume that they're modeling high-level cognition rather than a low-level cognition, and often humans' intelligence rather than animal intelligence. So there's some differences there. Yes, a pause.
Sorry about this. This is we just need to change over.
So did that not get broadcast then, the slides? Okay, I can go back. That's still early.
Now they're seeing.
Okay. For those that missed, whoops, I'm going, hang on. All right, there was the architecture, related concepts, and then now about cognitive systems. So there were 6 basic assumptions that Langley outlined for the community. One was commitment to high-level cognition. Another, structured representations, often complex hierarchical representations. In cognitive systems, it's basically, it's not a bit vector or a simple vector of numeric values. Rather, it will be schemas or other hierarchical symbolic representations are the commonality for a cognitive system. Also, rather than optimizing, it is building a system that uses heuristics like people do. We often don't have complete and consistent, we don't do, well, let me see, I should just say often our solutions to problems as a human are good enough. That is, that they're satisficing and they get us through, they solve what we need in terms of a solution to a problem rather than the optimal perfect one. And there are reasons for that. But there's also a number of links to human cognition. Many of the cognitive architectures actually model human data, in particular. MIDCA actually does not have a big commitment to modeling human data per se, but it is inspired in many ways by human performance and human behavior, and has certainly a relationship there, but we don't model in particular data that would be collected from human subjects, for example. And the research is often exploratory in that certain theories, certain cognitive architectures have a theory of how cognition might work, and are exploratory in the fact that often they're early, well, it's not simply preliminary, but they're looking at a very complicated space and testing hypotheses in a way that often are not as formal, and they can be rigorous, but they're not often as narrow. They're broad hypotheses that test in more of an exploratory way. And I think this paper will explain that more clearly. Though there are a number of cognitive architectures, I'm going to list 5 here, and I apologize to many EPIC and many of the other architectures that are out there, but 5 that are I will briefly discuss today in terms of the relationship to MIDCA are ACT-R, which is out of Carnegie Mellon University, SOAR, University of Michigan, and it originally came out of CMU. Icarus at ISLE, and Clarion, Ron Sun, that's RPI, and MIDCA here. Icarus, as far as I can tell, doesn't actually have an acronym. I did want to mention too, SOAR, that was the original acronym, State, Operator, and Result. I believe that is no longer the case. They use it less as an acronym now, but I thought I would put it there for historical purposes. I want to broadly look at each very briefly and look at what their commitments to a cognitive architecture means in a very small way, usually through a quote. So I have listed in this presentation, I mentioned, I think the slides are going to be made available afterwards as well, but I've listed a number of publications that give you a little bit more details about what we're talking about, and some links to all of these architectures. The URL is provided as well. So back in 1991, there was a workshop or symposium at Carnegie Mellon that was held on architectures for intelligence. And there, I think ACT-R, SOAR were both presented, as well as Prodigy, and Tom Mitchell was there. I don't remember, Theo, I think, was the architecture. John Anderson had a chapter, the very first chapter actually, in this book that came out from the conference, and he gave this principle of rationality. So his architecture, by the way, is ACT-R. It used to be ACT-STAR, but the principle of rationality changed it. So the R in ACT-R stands for rationality. This principle is that cognitive systems, the adaptation of its behavior for the organism, whatever you're modeling. And so optimization is, well, yes, it depends on how you would define that, but essentially we adapt our behavior to learn and improve when things occur in the world. And he gives, for the kind of, for this principle, under this principle, when you're wanting to use a cognitive architecture, you first have this rational analysis. The first three steps are to specify the goal that you're trying to model for this cognitive system, the set of goals for the behavior that you're modeling with the architecture. You develop a formal model or a computational model of the environment that the cognitive system would be within, and make some assumptions about the computational cost, right? There's not only a cost to behavior, but there's a cost for thinking. And given those first three steps, you then derive a function for that, or a model in the architecture of that behavior. So your behavior might be planning, or your behavior might be text understanding, or it's something more narrow. For ACT-R, I believe they also looked at modeling human reaction time and memory experiments. So it might be simply memorizing a list of 5 words and then recalling one word that may or may not have been in that list after so many seconds of seeing it and then not seeing it. So that might be the behavior that would then be modeled. You then test that and either confirm or disconfirm the kinds of predictions that come from your model when you look at how people would do it. And if there is a discontinuity there, you would iterate and try to improve what your assumptions are, your formal model, what goals, how their goals are represented, or exactly what the goals are. You have ways to just iterate on that. Given that, then ACT-R has this kind of a structure. It focuses on memory in terms of a declarative and a procedural memory. Declarative memory being the memory for facts or concepts, or skills or behaviors, or how to do an action would be our procedural memory. How to ride a bike is less a step-by-step, well, I raised my foot by so much, it's whether I can just perform that. And so there's a long-term memory for both declarative and procedural, and that you can retrieve from or execute items from memory. You have a working memory from within. You do matching to your long-term memory to have to retrieve items for performance given some input encoding. There's a sensory register where the input comes from. So this is an abstraction too. There are a lot of details. The model is in a production system, or it's rule-based. You define the rules. That's kind of like the programming language for a computer architecture. Here you would define the rules for the behavior model that constitutes the behavior model. And then those rules would be matched from memory. You retrieve them and then execute the rules for behavior and see how it would operate given input from the performance. So now that touched on, he had a cognitive architecture. He talked about a cognitive system. There was a little bit synonymous. In a very interesting paper, though, later in 2009, that Anderson paper was 1991. Here, Langley and Laird, John Laird and Pat Langley and Rogers had a very good paper about cognitive architectures, and they defined it in terms of 3 characteristics: an intelligent system, or for the agents. So the cognitive architecture specified a fixed domain independent infrastructure that consisted of memories, both the short and long term, memories that store knowledge or content about beliefs, goals, and knowledge. The representation, how those elements are actually represented in the memory for larger scale structures and how they're composed. And then the functional processes that actually operates on the knowledge that would produce an output given some input. So those are 3 important things I think you will find in all architectures, either more or less. For us that are in the MIDCA community and that are intimately familiar with MIDCA, the representation, for instance, that we would have for a shop operator or to create a domain, the documentation helps explain that. And we know Dustin went through the functional processes, but the memory model here is actually weak in MIDCA. But that is something I think that is forthcoming, where it's highly developed in most architectures and a large focus. Here we have SOAR model. You can see again a procedural memory in long-term memory, also semantic, and then episodic. So semantic memory is like an ontology, the concepts that we know about. Procedural, again, is the skills that we have. Episodic it's a memory of the actual actions that the individual performed in the past or currently, and we would store that. And it also has a symbolic working memory. It has a very sophisticated spatial visual system that has been connected with cameras, systems, and robots in the past, and produces action. So there's a lot of similarity here. Unlike Act R, what is modeled is often not necessarily human data, and certainly usually higher level cognition and performance, for instance, on a robot behavior rather than reaction time studies. It's at a little different level than Act R, but there are a lot of similarities there. Icarus also contains a number of the same things: a memory for concepts. This is a declarative memory in beliefs. It has a perceptual buffer as well. Skills here are distinct from concepts, but are represented in the same language or the same representation here. So there's it's slightly different, but very similar to the others that we've seen. Then there's a separate architecture definition by Ron Sun. He has a architecture called, but this is a very similar definition as well. He says that a cognitive architecture is broadly scoped, it's domain generic or domain independent. It's a computational cognitive model and captures essential structures and processes of the mind to be used in broad, multiple level, multiple domain analysis of behavior. So I think that is very consistent with what we've seen both in the principle of rationality, previous definition. Here, Ron Sun does distinguish though it's not in this quote, it distinguishes between implicit knowledge and explicit knowledge. So I can show you that. This is Clarion. There are 4 main parts. There's an action-centered subsystem about behavior and skills and so forth. There's an explicit representation of actions and implicit representations. This is the upper left in blue. There's also non-action centered explicit and implicit representation. This would be for concepts, and instead of about behaviors, it could be about new concepts and learning facts. You would, for natural language, I believe that would be in this component. You also have a motivational system. Now, this is the lower left, in which goals originate from. So there's both an explicit goals that are structured here, and there are implicit goals that emanate from drives of the system, basic drives. And then there is a metacognitive subsystem. So as Dustin mentioned, there is a commitment to metacognition also in this dual cycle architecture MIDCA. It is different here. The system, I believe, is subsymbolic or neural net based. The implicit representations in Clarion are neural nets. The explicit are rules, again, like productions or a rule-based system. So there's still commonalities. There is this is one of the architectures, other than MIDCA and Clarion, I think few really look at metacognition specifically. What is done in metacognition here is, as I understand it, it's more about goal setting rather than originating the goals. I believe this is selecting the goals. It's similar to the intend function. More information can be found at the URL below at Rensselaer Polytechnic in New York. So I wanted to switch to our take on cognitive architectures and all of this cognitive agents and related concepts in the MIDCA, the little mid community that we have here. And I can think of it as, my thought was to think of it as a perpetual goal-driven cognitive agent. We have less of, I mentioned, we have less of a commitment to human data per se, but more about agents that do things in the world, whether it's a robot or a model of a human. I don't think we're all about robots alone, even though, oh, and that was, by the way, the thing I forgot in the mini, one of the new things was the interface to ROS. I think that was really implemented this year. I'm not sure that we had it at last year's workshop. We did have it already by then. Okay, so I stand corrected. Anyhow, I did want to make a plug to it. But let me go back. If we're saying a perpetual goal-driven cognitive agent, what do we mean actually? Instead of a cognitive system, a cognitive agent, well, I would claim, well, actually, Hewins and Singh claims the cognitive agent is some intelligent system that uses knowledge structures, goals in an environment in which there's perception and action. So agents are ones that find themselves in some environment, whether it's a software or a physical environment. It may be a software agent rather than just a robot, but there's some environment rather than just mind games. It's embodied in some sense. And then goal-driven autonomy. There's a real commitment from this notion of what we call here goal-driven autonomy and more broadly goal reasoning in the MIDCA community. And I think this is one of the places where it started. And that's one of the focus of the metacognitive or the MIDCA architecture is that we don't just wait to be told. Agents, a MIDCA agent can generate their own goals given some anomaly that it would perceive. So it can recognize when there's a problem, possibly explaining what caused the problem, and then generating a goal to remove that cause. And there are some citations here that can point you to more about that commitment, but perpetual is simply just agents that would exist over long durations. And we've had some work. It would be, I think the ideal would be to have an agent turn on the robot and have MIDCA use it for a month. John Laird wanted to have a SOAR agent that had a memory of behavior over a year. And I'm not sure, but with the episodic memory that they worked on a few years back, they did have extremely long episodic traces or memories of continuous action. We have not done that kind of experiments like that, but we have put in place, and we, I think the the algorithms or the procedures, and certainly have thought about what it takes. That drives our research. Really, if you have a long for which an agent needs to be independent, things will happen that they don't expect in long durations, and you need to be able to react to that and manage it without to avoid catastrophe. Then this was the architecture. Dustin talked about it a little bit. I wanted to point out one very minor thing. I think his architectural diagram was from a little bit from last year. So in the perceive phase in the lower right in orange there, rather than claiming that this would be outputting a percept, I think within that, we would have a perception from the environment, and we generate out of perceive is a state in terms of predicate relations. If you're working with Ross in the environment, that's a very big problem, actually. Zora's, Danenauer's work has distinction there, and it's a minor one, but I just wanted to point that out. So as a cognitive architecture, as a cognitive system, or as an agent, I think these are the main points in which MIDCA makes the connections to other work in these related research areas. The 6 assumptions of a cognitive system, other than I had pointed out, it's a weak link to human data, more inspired rather than trying to model human data. I guess, well, that was in the principle of rationality, but the 6 assumptions for a cognitive system were generally met. It adheres weakly to the principle of rationality. We do focus on what the representation is and what the processes are, what the function of those processes are, that is their input and their output, and what is the transition, and but not memory per se. The 2 big points, how many minutes? 3. The 2 big points, though, is that the MIDCA architecture really constitutes a computational theory of high-level autonomy, what it takes for an agent to be independent, generate its own goals, not wait to be told what to do. And secondly, it does center on goals and metacognition in particular, and I think that distinguishes it. But I can't emphasize more of the commonalities with it. These are the conclusions I think I've gone over, and to be on time, Robbie, you can come on up. Just to reiterate, there's a lot of commonality here, and we do share with all cognitive architectures. We differ. There were a number of examples that we covered, and hopefully we will have coming out in this following year a version 2 of MIDCA. We shall see. Thank you.
Thanks, Mike. So we are now going to transition to Shravia's talk. So just bear with us a moment as we yeah, so I'm just gonna screen share and just gonna all right. Okay, so I'm going to pass this over to, let me just go back to the Google Hangout, make sure, okay, everything seems to be working. Okay, please welcome Shravia Kandrakunta. She's going to talk about goal graph and goal operations in MIDCA.
Hi everyone, I'm Shravya and I'm going to discuss a few points about goal graph and goal operations in MIDCA. So let's get started. A goal graph. A goal graph is a data structure which organizes and manages all the goals of the agent in a hierarchical format or a tree structure. The current goal graph in the MIDCA has three classes associated with it. The first one is the goal, the second is the goal node, and the third is the goal graph. The goal contains ID and arguments, which means the ID is the predicate of the goal and the arguments are the objects related to that predicate. And then the goal node contains four objects within it. The first one is the goal, the second one is the parent set, the third one is the child set, and then sorry, the children set, and the fourth one is the plan to achieve the goal. And then the goal graph contains all the relations between the nodes. That is, it might be a single node might be a parent to some other node, or it can be a child to some other node, and all those things. So the goal graph structure helps the user and as well as the agent to prioritize all the goals which it has. So let's take a look at how the goal graph is working. So whenever the MIDCA is initialized, an empty goal graph is also initialized with MIDCA and is pasted into the memory of MIDCA. And whenever these new goals are inserted or inputted by the user or by the agent, the MIDCA performs goal validation on those goals to check if the goal is really valid one or the correct one. And then if the goal passes the goal validation test, then those goals are inserted into the goal graph in the memory, and later on fetched from the memory, acted upon, achieved, and then removed from the goal graph. So let's take a look at this in detail with the help of the MIDCA architecture. So here the perceive phase does not have any interaction with the goal graph. It just currently observes the world and updates the states of the world into the memory. The interpret is the one which gets all the goals. Those goals might be the user provided one, or generated by the agent itself. And then the interpret only validates the goal based on by checking the ID and arguments of the goals. It initially checks if the ID belongs to the domain file defined in MIDCA, and arguments are already in the state file or not. And if these two tests are passed, then the interpret goals, then the interpret phase inserts the goals into the goal graph and stores it in the memory. And then the evaluate phase checks to see if the goal is achieved or not. If the goal is achieved, then the evaluate phase removes the goal from the goal graph. And the intent phase is where the goal selection operation happens. We'll talk about the goal operations in the next few slides, but just to make sure, the intent gets all the goals from the goal graph, and then selects some goals based on some criteria, and inserts those selected goals into a stack called current goal stack. And then the plan gets that current goal stack, and then checks to see if a plan already exists for that current goal. If not, then it would generate a plan and insert it into the goal graph. If a plan already exists, then it does nothing. And then the act phase iterates through the plan and executes each action at a time. And in the meta phase, in the meta phases, the plan also interacts with the goal graph in order to perform the goal transformation operation, which we'll talk in the next slide. So if you want to better understand the goal graph working with the example, please take a look at the previous year's demo. It'll be more clear than here. And so here are few goal operations which are already implemented and are yet to be implemented in MIDCA. The first one is goal formulation. The goal formulation is when the agent generates its own goals without the help of an external user. The goal selection operation happens when there are more number of goals to achieve in front of the agent, and it is not in a state to achieve all of those. And then then the goal transformation operation happens for several reasons. One of the reason is the lack of availability of resources, and the other reason might be some other goal is more important to the agent than the goal it is working on. And then the goal delegation is the operation of the agent delegating its own goal to some other agent or the user himself, because it comes into its knowledge that it is no longer in a position to achieve that goal. And then goal achievement checks to see if a goal is achieved or not. And then the goal monitoring, this is the work of Zora, and she's currently working on it. It checks to see if the reasons to achieve the goal are still valid or not. So let's go into detail. Let's talk a little bit of detail into about some goal operations here. So the goal selection operation, as I said earlier, this happens when the agent has a choice of multiple goals and it cannot achieve all of those. So after knowing this, we come to a question, and we come to a question on what basis do I choose. So here in MIDCA, we have used we have implemented this of performance to limiting factor, where the performance and limiting factors are domain specific, but the estimates of the performance and the limiting factor are estimated by the agent, uh, uh, by the by the agent. We call this smart selection criteria. You and This idea is borrowed from Johnson. His work was very domain specific, and we tried to generalize the work to different domains. Let's take uh, look at some a specific example to better understand this criteria. So here, let's take a look at the construction domain example. Here, the agent has two goals to construct the building B1 and the building B2. So for each goal it achieves, it would be given a credit, say 1, and the limiting factor here is time, and the agent should complete all of the goals within its time limit. So to be more clear, to place the block A, the score it would achieve is 1 here, and then the time taken to put the block would be 1, and for the B and also the block E, the score would be 1 and the time taken would be 1.2, and it is the same for the other one. And as the height of the tower increases, the time taken to place the block also would increase. The time and the score are currently provided by the user. So if we take a ratio, the ratio of performance over the time for building B1 would be 0.88, and for the building B2 it would be 0.9. And if the agent had all the amount of time in the world, there is no need of this goal selection operation, because the agent could do each and every could achieve all of its goals one after the other. But in the real world, this would not be the situation. So let's say if the dead if the agent is asked to to achieve these goals within a deadline of say 5 seconds, then then the agent is forced to perform the goal selection operation. And in our method, it would select the building B2 because it has the performance over time. Earlier it was the minimum ratio, but then we changed it to the maximum ratio in order to maximize the performance rather than uh, checking it for the time being. Oh, sorry. Okay. So that was the goal selection operation. And the goal change operation, this currently is implemented in MIDCA whenever the MIDCA is out of the resources, or whenever the MIDCA encounters any emergency situations like the tower being on fire or something like that. Uh, so even this is implemented in construction domain. So we would call that a tower is stable when the tower is constructed with the help of motor, and we would say the tower is not stable or wobbly if the tower is constructed without the help of the motor. So this is implemented in the control phase, that is the meta phase of the MIDCA. So the MIDCA would be given a certain number of motors, and then it would be asked to achieve all sturdy towers. So it has to use only the stable ons, after certain time it would be out of motors, and then it has to it would be out of motor, and it would be left with any choice. So there comes the goal change operations, and then the agent would itself change the operation of stable on to on, and then complete the construction of the tower without the help of the user directing it to change its goal or anything. So we have implemented this goal change operation using predicate transforms, where the generalization means moving into more generic predicates, specialization means moving into more specific predicate, and identity means uh, stay selecting the same goal again. And abstraction is similar to generalization but for objects, and concretion is also similar to specialization but for objects as well. So this is how, with the help of predicate transform, we have implemented the goal change operation in MIDCA. And the one more important operation happening in MIDCA is the goal formulation. MIDCA is able to formulate its own goals whenever it encounters an anomaly. This happens in interpret phase of the MIDCA. Whenever a block is set on fire or something, then the MIDCA generates its own goal of putting off the fire, and then it gives it the highest priority. Uh, so that's it. So let's take a look at the future work here. We are wanting to introduce a new variable or something called goal type, which would say which would associate the type of the goal into the goal graph. We think that this with many other factors would help in integrating or making the goal operations more flexible. And we also want to make the all the goal operations work simultaneously. Currently these operations are implemented, but all of those are independent of each other. And these are also domain specific, and we are trying to bring everything to every domain uh, till now. And so that's it. Thank you.
Thank you, Stravia. So we are now going to get ready for our first remote speaker, James. So, James, are you there?
Yeah, can you hear me?
Okay. Yes, we can hear you. So I'm going to go ahead and pass over. Are you ready to go?
Yeah, I'm going to work on the screen share. Hold on 1 second.
Okay. I'm going to give you the. I'm going to make it so that you're presenting to everyone.
Okay. All right, can everyone see this and hear me?
We can see you and hear you.
All right, you can see the slides?
Yes.
Okay. So I'm presenting on how we've been using MIDCA to enable intelligent rebellion in autonomous agents. It looks like I'm the first one that's more of a separate application and less of the structure of MIDCA itself. So I'm James Boggs. I'm an undergraduate senior from Union College in New York. And I've been working with Alexander Coman and then Dustin Dannenhauer to do some intelligent rebellion and rebellious agents kind of work. So rebellions, it's sort of sketch. A lot of people go, why would you ever do that? That's how we get Skynet. But actually, rebellion's kind of useful. So a rebellious agent in general is one who rejects an operator's command or order. So humans can be rebellious agents too. And in real life, we often are rebellious agents. So in real life, we rebel when we see something going wrong and we say, actually, no, I'm not going to do this because it's going to lead to a bad result. Problems with what we're doing. So I'm not going to do that command because there are ethical problems. I have issue with what you're telling me to do. I won't do it. And then there are things like self-expression. When you say, I personally just don't appreciate that. That's not the kind of thing I want to be doing. What you're telling me to do. And robots can get sort of similar benefits to that by rebelling against certain goals, if we can get them to rebel properly. Rebellion is useful in real life. So consider some rebellious situations when a human might be rebelling. And I'm taking a lot of these examples from a paper by David Aha and Alexander Komen in 2017, which sort of presents a motivation for rebellion. So in one situation, an actor in a high school film project is arguing with her director about the way in which her lines should be delivered. So the actor, having like practiced the role and understood the character, is in somewhat of a better position to understand how the character is feeling and thinking at the moment. And so by arguing and rejecting the director's directions on how to deliver a line and imposing her own ideas of how the character should deliver the line, she's actually enhancing the character's believability because she has a pretty good understanding of the character's background and motivations. So that's a net benefit from her rebellion. Then maybe early on in her career, an employee expressing her preference to like not take on a new position or to not get a new management position, for example, can be sort of an instance of self-actualization where the employee says, I don't see myself as, maybe the promotion is to like a manager. I don't see myself as a manager. I want to learn more. I don't feel like I'll get much out of the position. And so she rejects a promotion or take up a different position because she doesn't feel like that really fits what she's looking for in her life. Then ethically, imagine that she's an established engineer and she's working on this project and her supervisor is telling her to hurry up, to hurry up the pace. But she recognizes that if she puts it out too soon, there will be flaws in it, which could lead to danger to people's lives being lost or at least to damages. And so she refuses. She says, I won't work on this project anymore if you're not going to give me the time I need to do it properly. That's sort of an ethical rebellion, which obviously will have benefits because people won't get hurt if the project goes wrong. And then there's sort of a social aspect. So imagine that she sees a social wrong, so she can lead a social protest campaign in support of her in-group or another person's in-group, which she feels is being wronged or being subjugated in sort of a social justice situation, which is a sort of a rebellion against society and ends up improving life for people in that group. And in these situations, the human is rebelling, and it's a clearly beneficial rebellion. This is the kind of rebellions that we want to encourage in humans. And I think there are similar situations in which a robotic agent rebelling gets some benefits. So there's not a whole lot of background research on this. It's a fairly new research area. Aha and Komen note that a general formal framework for AI rebellion doesn't exist yet, and that was in 2017, so that's fairly recent. There is some motivational work and example scenarios for rebellion, and the ones I actually cited in the last slide were from the AI Rebellion Changing the Narrative, the Aha and Komen 2017 paper at the bottom there. But there are several other papers that you can find good examples of why we might want to investigate intelligent robotic agent-based rebellion. So the topic of the topic of the conference is why MIDCA and how do we use MIDCA? So we started out with MIDCA because it's Python-based. I already knew the language, which is a big help. But there are also, of course, lots of libraries. It's easy to test and prototype in Python. Benefits of Python. You can go online. There's all kinds of nigh on religious stuff about how Python is so good. But it's also metacognitive. So it's focused on introspection on goals and figuring out at a meta level which goals are appropriate and how we might want to change goals and change the way we're thinking about goals. And that seems to be where rebellion fits for me. I see that as a very natural place for rebellion, is at a meta level, considering the goals themselves, with a sort of a meta goal of being true to yourself or being ethical, these kind of things. It's also modular, so that was a huge benefit. It means that we don't have to, as I believe Dr. Cox mentioned, it's a framework, it's an architecture, so we can add things in, we can create modules without having to redo or recreate an entire like framework for it to create a skeleton. So it provides us a baseline, and then we can just add in new modules that enable rebellion without worrying too much about the inner workings. So in our rebellious agent, MIDCA is used as the agent, as the base agent, and the rebellion itself is currently happening in the interpret and evaluation phases, which is not at the meta level yet, but that's kind of where I felt it fell naturally within just the cognitive layer. And at the time we started working, the metacognitive layer was still under development. So we added some rebellion modules, which mesh pretty well with the existing MIDCA code that we found in the code base. We did rewrite most of the other modules to fit in with a new scenario, but it was essentially just adapting some of the modules that come with MIDCA to our new domain. It wasn't particularly strenuous. The interesting part was definitely the new modules that we developed for Rebellion. MIDCA's memory and goal graph, the access to these kind of tools was really important to us. So that was a huge part of our usage of MIDCA was with these things. And then again, MIDCA's modularity, the ability to create modules which enable rebellion without worrying about other things like perception, planning, and acting. That was a big benefit. And that was part of why we used MIDCA. So here's kind of a diagram of how rebellion works. And you'll it's pretty standard MIDCA. So the important part starts at the interpret phase once the agent has already had a perception of the world. And the agent interprets this perception of the world in light of goals and evaluates, and then can evaluate how goals need to be adjusted or changed based on this interpretation. This is pretty standard MIDCA stuff. And so up to there, we're about the same. But part of the interpretation is now appropriateness. It's not just how are goals physically affected in terms of its ability to complete them, but how have goals been affected in terms of its willingness or the appropriateness of a goal to be completed. So we can evaluate this interpretation and decide that each goal is acceptable, in which case it goes ahead and plans and acts and carries out the goal, or impossible, in which case a goal, or it might remove the goal from the goal graph. But that's also a fairly standard thing. But it also might evaluate a goal to be undesirable. And that's kind of where rebellion comes in, because the goal is still possible. It could carry out the goal, but it might not desire to carry out the goal. And that begins the rebellion part. And so as part of the rebellion, it sort of evaluates why it's rebelling. It looks at the goal and remembers the goal, but it also looks at like the scenario surrounding the goal, what caused the rebellion. There are multiple operators, gave the goal that it's rebelling against, information that you can use to glean why and what it's rebelling against. And it gathers all that up, and then it actually informs the operator who gave it the goal. Critical part of rebellion, of useful rebellion, is a dialogue between the agent and the operator. And the operator, it informs the operator of its rebellion, and the operator can then accept or reject the rebellion. So if the agent rebels and the operator says, okay, that's a good idea, we shouldn't do that, you're correct to rebel, it just goes on and removes the goal from the goal graph or adapts it into something which is acceptable. If the operator says, no, you can't rebel, I'm forcing you to do this, then the agent actually has a choice, because the agent is ultimately the troop on the ground or the actor in the situation. So the agent can actually still rebel. It can consider this rejection from the operator. And if it rejects the operator's dismissal of its rebellion, it can still remove the goal and say, I'm just not going to follow your directions at all. But it could also say, well, my operator is really enforcing this, so I feel like I must go ahead and do it, even though I have reservations about the goal itself. And then it accepts the rejection and goes ahead to the plan, the intention, plan, and action phases. So there are two phases that are particularly important and have come up a bunch in the rebellion: the interpret phase and the evaluate phase. These are both part of MIDCA itself. They are inherently very surprising, but we've added a little bit to them. So the interpret phase in MIDCA normally interprets the world in light of its goals. It looks at the percepts that it just got, says, all right, how have these affected the goals? Rebellion adds appropriateness as a thing. So in addition to impossibility or the needing to change a goal, it also says its goal is inappropriate. The evaluate phase is then used to look at how goals should change in light of interpretation, how we can alter goals or come up with new sub-goals. Rebellion adds agent-operator interaction as a means of sort of judging whether a goal is really worth rebelling or figuring out how we can adapt a goal to make it less undesirable and more appropriate to carry out. So the interpret phase in particular, as I said, MIDCA uses it to interpret how new percepts may affect the goal. Rebellion, in this case, is whether a new percept has changed whether a goal is appropriate or not. So in our domain, we model agents as military drones and operators as sort of troops on the ground who are instructing these drones. And so if a new percept says, oh, there's a civilian in the area, that might impact the ethics of its goal to eliminate a target. And it says, oh, this isn't appropriate anymore, and then it passes it on. It remembers that this particular goal has a problem with appropriateness in particular, and it moves on to the evaluate phase, which like normal MIDCA is used to evaluate the status of goals and kind of resolve the problems either by removing the goal or by changing it, reevaluating it. And rebellion that's inappropriate are now evaluated into how can we make them appropriate, or do we have to just get rid of them? So once such a rebellious goal is found, or a rebellion-inducing goal is found, the agent can sort of evaluate why is it worth rebelling, what is the agent specifically rebelling against in this situation, and then inform the operator. Because we want the operator, again, we want the operator to be party to this kind of rebellion. We want the operator to have some amount of say in why isn't it appropriate, what can we do to resolve the appropriateness of the rebellion. So if a goal which was interpreted as killing a civilian, which makes it inappropriate, there might be alternative goals that the operator is aware of, and it's rebellion worthy, and then they can communicate about this. So there are actually two parts here. First thing is establishing the rebellion, which is figuring out why it's inappropriate, analyzing the situation, gathering all of the information which the agent uses to make its decision to rebel, and any information which might be useful in altering the goal and creating a new goal. And then it communicates the rebellion with its operator, including all the relevant information, any kind of new goals it's come up with on its own, and then asking what it should do, whether it should actually rebel, and what it might be able to do in the future. So this communication, I'm kind of speeding through here because I want to get us a little bit back on time, but this communication is enabled in our instance using TCP, which I added on here just because it's an interesting thing that I haven't heard about with MIDCA. But essentially, we wanted each MIDCA agent to be running separately and removed from the world. So there's a few benefits to having them operate in separate processes. At the core, it isolates the world information from the agents. So the agents have no direct access to the world information. The interface between the two over TCP really allows us to control exactly what the agent can see and what they can do. And this makes it much easier to implement partial observability. And it also kind of makes it more accurate to the real world. So in real life, of course, the agent and the operator aren't on the same local machine. They're communicating over a network somehow. And there's only so much that information that the agent can communicate to the operator at each given time. So we added some TCP communications into the modules themselves, which can pass actions or messages from other agents or even observations about the world back and forth. So the way this kind of works is that the world is a server, a TCP-based server, and each agent can pass requests back and forth to the server. Things like, what does the world look like to me? Actions, I want to do this in the world, or messages to other agents, like I want to tell my operator that I'm rebelling. In the future, we might look at adding a more robust kind of communication system outside of each individual model. That modules can access similarly to the way that they can access memory or the goal graph, things like that. But I just thought that was an interesting aside. So our actual research imagined military drones as the rebel agents in question. So kind of agents or operators in autonomous situations, and the reason for the rebellion is ethical rebellion. So a rebellion happens in these situations when the agent sees a civilian that's threatened by their goal, where their goals are usually the elimination of enemy targets. And you can imagine that from drones, the possibility of harming a civilian when they're eliminating an enemy target can be kind of high sometimes. And that's like ethically very worrying. So they are programmed ahead of time with the ethical desire to not harm civilians. The world itself is fairly simple. It's just an n-by-n grid where we portray agents, enemies, and civilians, and they each take up a tile. And agents can actually fly over enemies and civilians and be on top of them. And the agent can detonate a bomb at its location, which has a certain radius of effect and eliminates enemies and civilians in that radius, starting from where the agent itself is. So it's aware of how far its blast will spread and which enemies and civilians are targeted. The operator is stationary. It doesn't actually see any civilians. It knows where the enemies are and can give goals to the agent, which introduces some amount of uncertainty and kind of motivates some of the rebellion aspects. The operator itself will just give a goal to the drone, say eliminate this target, and the drone itself will carry out the action and then rebel if necessary. The drone and the operator agents can actually have different personalities. So rebelliousness and resistance, where a drone is more rebellious if it's more willing to override its agent or its operator and say, I don't care what you say about my rebellion, I'm going to rebel anyway. Whereas an operator is more resistant or resolved if they are more likely to reject an agent's rebellion. So if an agent, which is highly rebellious, rebels, and then the operator says, no, you can't rebel, the agent's very likely to say, I don't care, I'm going to rebel anyway. And if an agent is highly resistant, or if an operator is highly resistant, then when a drone rebels, the operator is much more likely to say, no, I don't want you to rebel. So this is kind of what the world looks like. It's not very pretty, but the blue objects here are agents, and the white object there with the white OO is the operator itself. So each agent and operator sort of has a range and a vision. You can see like the yellow box here is the vision range of the agent A1. So right now it can't see any enemies or civilians. But as it moves around, it starts to learn more about the domain it's in. It starts to see more of the map, and it actually remembers everything it sees. So this allows it to proactively rebel, which I'll get to a little bit later. But it allows it to proactively rebel where if it remembers that a civilian is in a certain location and it sees another agent going that way, it might be able to say, actually, there's a civilian over there. But yeah, at the moment, you can see the green civilians and the red enemies. And in this situation, a bomb has a radius of 2. So everything in that yellow box, if the bomb went off at A1, that's every place that would be destroyed. So the operator can say, for example, take out the enemy at 5,3, which is sort of right there. And then once the agent moves forward a bit, it'll recognize that the civilian is in the blast and actually reject that rebellion. So that's kind of just what the world looks like. And then we got some interesting results by running that experiment a bunch of times. So these are heat maps, which actually come in pairs. So each pair of 2 is a different scenario, where the first of the pairs is the percentage of enemies which have been killed successfully in the operations. And the second of the pairs is the number of civilians which have survived to the end of the operation. And then this first top left pair is all operations that we ever ran, all simulations that we ever ran. But then the remaining 3 are kind of broken up by how dense the enemies and civilians were. So low density over here means less civilians and enemies on the map and more spread out, whereas here, more civilians than the enemies on the map, and they're kind of clustered together. You can see the x-axis is agent compliance. So at 0%, the agent will never accept an operator's resistance to their goal. So an agent here will always rebel no matter what the operator says in this communication. Whereas an agent with full 1.0 compliance will always accept the operator's decision about their rebellion. And the y-axis is the operator's resolve. So an operator who's always accept and counteract it. An operator who is 100% resolved will always reject the rebellion no matter what. And we came up with an interesting pattern here where as operator resolve increases or as agent compliance increases or both, you get more enemies killed. So the lighter, brighter colors are higher enemies killed, but you get less civilians surviving. So if you prioritize civilian surviving, you want less compliant agents or less resolved operators. But there is actually something more which comes out as you break it down to low, medium, and high density, which is that, I guess kind of intuitively, the higher the density, it makes a difference of agent compliance and operator resolve. So at the low density, you can see that the gradation from low agent compliance and low operator resolve to high of those two, high agent compliance and high operator resolve, isn't as severe as it is down here in the high density maps. So you can actually afford in a low density situation for an agent to be more compliant and for the operator to be more resolved, and you'll get kind of greater success with less damage. Whereas in a high density situation, you want the agent to be very careful, you want the operator to be very flexible. Otherwise, you have a higher percentage of civilians who are driving the operation, which is obviously pretty undesirable. And then we also graphed some of these linearly, but I don't have that on the slide. So kind of moving into the future, there are some various possibilities for where we can go with agent rebellion research in particular. The first thing, and I think perhaps the most pertinent to MIDCA, is moving the rebellion to the metacognitive layer, which I think is really where it belongs. It'll mean faster rebellion because the metacognitive layer is running consistently so that in every cycle of the cognitive layer, it's evaluating its goals and what's going on with its goals. So that it can kind of change up. If it sees a reason to rebel, it can do that very fast. But it's also more natural, I think, to have it in the metacognitive layer. Because it's not, the rebellion is not about changing goals in order to be able to do them. It's because you see something wrong with the goal itself, and you see something wrong with the goal process. So it's very much more a meta-analysis than a cognitive initial, first layer analysis. But there are other aspects that we might want to look into too. So agent history and narrative as aspects of rebellion is particularly interesting because people have different histories. Real people have different histories and rebel against different things and also different ethical systems. So we can explore very much the narrative AI kind of aspect of this by having rebellion based on the personal history of each agent. But there's also social aspects in real life on rebellion. So people might be more or less likely to rebel based on peer pressure, where they feel pressured either to conform or not to conform based on those around them. And similarly, an agent might be less likely to rebel if they trust their operator versus if they don't trust their operator. That actually works in reverse too. So if you think about an operator might be more likely to give a goal to an agent it trusts to not rebel and not reject its orders. There's also sort of a learning aspect here where we might want agents to learn the consequences of their actions so that they aren't initially told every situation explicitly in which they rebel, but they're given a set of values, for example, human life. And then they learn based on experience what things they shouldn't do and what things they're uncomfortable doing because they've counteracted their own ethical guidelines. I think that one's particularly interesting because that's very much how humans tend to do it, is we tend to learn what we're uncomfortable with and then not do that again. There's also something, I mentioned something earlier here, which sort of ties in with the social rebellion, which is the proactive rebellion, where an agent might actually ask another agent to rebel. So if an agent has already rebelled against taking out an enemy which will endanger a civilian, other agent who now is going to try and do that, wait, you shouldn't try to target that enemy because there's a civilian in the way, that's wrong. So there's a little bit of proactiveness, a little bit of peer pressure there that we can explore further. And finally, my experience with MIDCA. Overall, pretty good. I was pleased to use MIDCA. It could use a little bit more learning resources. I was watching the previous conference, and that helped me a lot. But a lot of the learning that I did still had to be sussed out from code. I still looked around at a lot of the example code, which is nice. It's nice that we have that example code. But it's also very modular. That was probably the biggest pro for me, was the modularity, the fact that it was a very solid architecture, that I was able to create custom rebellion functionality without really disrupting too much of the other functions of MIDCA. Some things that I might suggest, and yeah, logging is probably the big one. The logging structure of MIDCA, at least as I found it, was kind of obtuse. There's a built-in Python logging library that I think would be pretty beneficial here. And then there's coding style, which is kind of nitpicky, I understand, but it's not mission critical, but definitely makes maintaining and understanding and learning easier. The coding style right now is kind of confusing and definitely disparate between various people, but I do understand that research code happens. And verbosity, there are settings in each module and at the initialization of a MIDCA agent for verbosity, but it doesn't actually do anything in the base MIDCA code. The verbosity is set in a variable in each module in each part of the MIDCA phase without reference to the verbosity parameter that's passed in when you actually create a MIDCA object. So yeah, that's everything. I managed to do that somewhat quickly. Dustin? Oh boy. Abort. Should I pass it back on over to you?
Yeah. So, okay. James, can you hear me?
Yeah.
Cool. Okay, great. Yeah, thank you for your talk. That was excellent. That was great. So we are now. I'm going to switch to me now.
Yeah.
Present to everyone. And share the screen. Oh, yeah. James, people are clapping here. They enjoy your talk.
Glad I was halfway decent.
Yeah. So, okay, I'm getting ready for my talk right now. Let me just share the screen. Okay. And so I just want to do a quick check to see if I'm on YouTube Live with my screen. Okay, and is it showing my slide? No, okay. It is now, okay. Okay, sorry, we are just doing a little tech because we're switching between speakers. So it looks like I'm screen sharing and presenting to everyone, and I believe you can hear me. So yeah, thank you, James, for a great talk. I'm excited to talk about MIDCA's architectural commitments. So my name is Dustin Dannenhauer. I'm the one who did the introduction. And so I'm currently doing a postdoctoral fellowship at the Naval Research Lab in DC. Yeah, so I wanted to talk about MIDCA's architectural commitments. So we heard from Mike about how MIDCA compares to other cognitive architectures. And sorry, I'm getting a little bit of an echo. I just need to, okay, I think that's better. Okay, yeah, I think that's good. Okay, I think we fixed the echo. Let me know, Zora, if it still is there in a minute. Okay, so right, MIDCA's architecture. Let's go ahead and get started. So in this talk, so I'm going to talk a little bit about MIDCA's architectural commitments, and I want to try to answer this question: why use MIDCA? So this is a question that I've gotten asked quite a few times over the last few months, and these questions, I think that one of the commitments of MIDCA is metacognition. And so then I'm going to go into some of my work on metacognitive expectations, and I'll talk about some future work. And part of this is to kind of, I don't know if we've really had a conversation about what are MIDCA's architectural commitments. I think that some of them are kind of obvious and clear from the papers, but there might be some other ones that we care about as a community or people working on this project. So if you are someone working on MIDCA so far, you might say, and someone were to ask you, what do you think MIDCA's architectural commitments are? These are some of the things you might say. So you might say that there's an underlying PDDL representation. So PDDL comes from the automated planning community and has roots even before that with strips and others. And so essentially it's a symbolic representation of a world where you have objects and you have operators that say how you transform a world state from another. So you can have an operator for like picking up objects and how that changes the world state. And just about every MIDCA example has some kind of underlying PDDL representation. So that's kind of consistent throughout. So maybe that's something we want to be committed to making sure we support PDDL. And I have a little asterisk here because we don't have the full PDDL. The other thing is the modular code organization. So that was a decision made by one of the earlier developers, Matt Paisner, and it's consistent throughout. And I really like it, and some other people like it. And so maybe that's something we want to be committed to. Maybe we want to be committed to having a modular structure. The other two are, I feel like, fairly obvious. If you look at some of the research papers, the strict order of phases that cycle. So this is interesting. So we have the perceive, interpret, evaluate, etc. And there's also both cycles, so cognition and metacognition. So those seem like kind of the core commitments. But the other thing, and Mike mentioned this as well in his talk, we should support goal reasoning. So as MIDCA evolves and grows in the future, all possible goal operations and goal reasoning should be able to be possible in the architecture, and the architecture should support that. So now, a little different, answering the question, why should someone use MIDCA? And so this has been, so this is kind of my attempt, and part of this last slide and this slide is to kind of generate some discussion. So any of you who've worked on MIDCA, note down like reasons. And I mean, we heard a few from James, but maybe this is something worth discussing in the discussion section at the end of the workshop. So my attempt is for one, I think it's great for research on metacognition and introspection. So from the ground up, MIDCA is designed to have metacognition as a core functionality. Another thing is that it's written in Python. So Python's really popular, has a lot of libraries, a lot of software, a lot of AI, data mining, machine learning tools are in Python. So for a lot of people, it's easy to pick up. And then the modular design, I like that. I feel like if I want to add some new components, it's fairly easy. At the bottom here, where I have this little future tag, this is kind of what I envision for the future of MIDCA. So I kind of have this dream where in the future, we can design cognitive agents in MIDCA. And when I say designing a cognitive agent, suppose you have some environment, you have some tasks that you need an agent to do, and you give the agent some knowledge about the world, what actions it can take, what kind of goals it should be executing. And all of that, for the most part, is in the cognitive level, the orange layer. And so because the metacognitive layer is meant to be independent from the world, right? It's just focusing on cognition. Perhaps you can get a lot of metacognitive functionality for free. And this might lead to more robust agents on the person designing the cognitive agent. So that's kind of what I see as a vision. It might be really cool. So potential benefits of metacognition. So this is a table from Mike's PhD thesis, actually. And this just shows some of the causes of reasoning failure. So I wouldn't say this table is exhaustive, but these are just some of the things. And all of these, or just about all of these, have to do with the cognitive level, right? So these are not obstacles or failures in the world. These are things that could go wrong at the cognitive level. And so my work has started before we can even get into dealing with the failures. How do we even know that one of these failures happens? And so, a goal selection failure, goal generation failure, knowledge selection, all of these things. How can we do so? So I've started to do some work on metacognitive expectations. So now I'm going to talk about some of the early work I've done. And part of this was done with Hector Mendoza Villa while I was finishing up at Lehigh. And and also MIDCA. So the main idea here is that we can treat cognitive processes like mental actions. So, and this is kind of the idea of drawing an analogy from planning actions and world states to mental actions and mental states. And a mental action is something that transforms one mental state to another one. So what is a mental state? So in MIDCA, right, so we so far, and Mike mentioned this, that MIDCA's memory is kind of weak. So for now, we kind of have a dictionary with certain kinds of variables that store data in memory. So a mental state for this purposes is a collection of variables. And we have a variable for the following. So selected goals, pending goals. And so we get this vector of length 7. Now, a mental action essentially performs reads or updates to the memory, and a mental state is like a snapshot of the memory. So before planning is done, before planning for a goal for the first time, in the agent's memory, it might not have any plan, but it might have a goal and a world state. And so that's the prior state. And then afterwards, it generates a plan, and now that's stored in memory, and that would be the post-mental state. And so some of MIDCA's phases have just a single module. So for some of these, they're just single mental action. But really, the focus of this slide is just to emphasize that mental actions are at the module level, because interpret, which performs the first 3 steps of the goal-driven autonomy process, where you detect discrepancies, explain them, and possibly formulate and insert new goals, that all happens in interpret. And so each one of these can be whole areas of research, and so each one of these should be its own mental action. I don't think it would make sense to consider all 3 of them together as a single mental. I think you care about reasoning at a finer granularity. So mental states are obtained through a cognitive trace, and so this happens in the monitor phase. And so this is an example of the intend phase, or rather the module inside the intend phase, which is just doing goal selection. So in this case, PG stands for, on the right here, stands for pending goals. And so there are 3 goals related to blocks in a blocks world domain. And SG means selected goals. And so what happens is, in this horizontal line here, this is where the mental action intend occurs. And so what we see is that in this case, all 3 goals have been selected for the agent to pursue. And then the next phase is plan. And the module in the plan phase, which is going to perform planning, has a world variable and a selected goals, and the mental state after is actually showing an empty plan. So this is actually what it might look like if we have a problem. We would expect this to be a plan with 1 or more actions that the agent's planning to execute. So just to show in the diagram where these fit in, the metacognitive expectations are in the interpret phase, and the trace is gathered in the monitor phase. So when I say a metacognitive expectation, what am I talking about? So essentially a function, this is what we have so far, and I think that moving forward, this will evolve and we'll have richer types of these, but even just this alone can be powerful. So we have a prior mental state, which is like a snapshot of the memory, a post-mental state, and a mental action. And essentially, the expectation holds or it doesn't hold. So it's either true or false. Example, when the agent generates a discrepancy, then the agent will generate an explanation for this discrepancy. In other words, if something surprising happens, the agent will be able to explain it. So if an agent can't explain why something unusual happened, that might be a problem where metacognition steps in. So this is how we would define it. These are, so if you remember before when I was talking about the mental states having a vector of length 7, these are 2 of the values in that vector. One is the discrepancies and one is the explanation. So at the bottom here, when the discrepancies is not null, when there's some discrepancy, we expect explanations to not be null either. And so the cool thing is that this is totally agnostic of whatever domain you're operating in. It doesn't care about the world. You could be flying a plane, drive, I don't know how you maneuver a sub, but maneuvering a sub, whatever that verb is, or driving a car, and this is an expectation, and this is a meta expectation. So we've done some experiments, and so this experiment is in the NBeacons domain, essentially a modified version of Mars World, which is something from some earlier work. Basically, it's a 10 by 10 grid, and there is an agent in the middle, and there are these beacons, which are numbered 0 to 9, and the agent is given goals to navigate to a beacon and activate it, and pits that it must avoid. This domain, and then the next domain I'll talk about, are fully observable. So the agent can see this, and so in the beginning, the agent will just avoid sandpits, no problem. But unknown to the agent and the agent designer, there is wind. So after some time, their wind starts blowing, and it has a permanent effect on the agent's actions. So whenever, think of wind as a kind of permanent change to the environment. I know wind in real life generally can change very quickly, but this is just kind of an example for this kind of behavior where domains change over time. So what happens with wind is that once the wind starts blowing after a certain amount of time, for the rest of the time, the agent, when it moves in the direction of the wind, so suppose the wind is moving east and the agent moves east, it will be blown an extra 3 or 4 tiles. And now the agent might find itself stuck in a sand pit. And so basically some of the planning domain knowledge could become outdated. So we implemented 3 kinds of agents. We did an ablation study. The first kind of agent, and so the last agent has these metacognitive expectations that I was just talking about. Specifically, it has the explanation expectation. So the first agent is a replanning agent. It doesn't do any discrepancy detection. So basically, goals are given to it. It generates a plan. It starts executing it. If it gets stuck in a sandpit, it just keeps trying to move where it thinks it's going to go until it's done executing the plan, and then it just tries the next goal. So it gets stuck easily, basically. Once the wind starts blowing, it's blown into a sandpit. Now we have a GDA agent, and this performs discrepancy detection at the cognitive level. So immediately know after executing an action where it gets blown and stuck in the sand, it'll perform an explanation that it's stuck, and then it will change its goal to become unstuck. And to become unstuck, it has to execute 5 push actions to free itself. So what happens is that the GD agent gets stuck easily, but it responds much faster. It doesn't try to execute a bunch of unnecessary actions before switching goals. Finally, the metacognitive agent has this, so it's has the same functionality as the GDA, but it also has metacognitive expectation. And in this work, we assume kind of an oracle function that knows how to update the planning operator. That's certainly an area for future work. But if we assume that we have that, because this work is focused on the expectations, how can we detect when we're in situations where we want to trigger metacognitive functionality? So essentially what happens is the meta expectation for explanation gets triggered, because what happens is that the agent gets blown and the agent can't generate an explanation for why it's been shifted. It only knows that it's stuck. And so it's able to update its domain knowledge because this metacognition triggers. So what we see is that we actually get a lower execution cost per goal achieved. So the replanning agent takes, so the y-axis here is execution cost, which is measured in number of actions executed. The bottom is the number of goals achieved. And so at the very beginning, they're all equivalent because there's no wind. And then what happens is that wind starts blowing, the replanning agent gets stuck, and then it's taking a lot of time because it's executing the rest of its plan, and then it's like, oh, I'm stuck. The GDA agent responds faster. The agent with the metacognitive expectations, it actually will update its planning operator so that it knows when it's going to move east, the wind is going to blow it, and it starts avoiding the sand pits after that. So this is one situation where in domains change over time, there's a benefit. And we did another experiment in another domain that has a similar property. So it has kind of a permanent change over time. We call this aggressive arsonist. So just for the sake of time, I might not go into as much detail, but happy to take questions or feel free to ask me later. This is based on the arsonist domain from Paisner and others from 2014. Essentially, it's the blocks world domain where blocks can be lit on fire. But in this one, after a certain amount of time, the arsonist just gets fed up. His fires keep getting put out, and he's like, you know what? I got to step up my game. So he uses a stronger fuel, and when he lights his fires, 2 blocks get lit on fire. And if the agent tries to put out the top fire, nothing happens because the bottom fire keeps it burning. So the fire is like burning up. So the only way to put out a fire once the arsonist becomes aggressive is to put out the bottom block. So if the agent doesn't learn that, and so in this we actually see stronger failure. So both replanning and GDA get to a point where all the blocks are on fire. And in this case, fire is a problem because the agent cannot pick up a block if it's on fire. And what's interesting here is that actually the GDA agent seems to achieve a little bit less goals, and that's partly because it responds quicker and it almost gets stuck quicker. So I'm just about ready to wrap up, and I just want to note this vision for MIDCA's future. So these metacognitive, so I've shown one metacognitive expectation for an explanation module, and so I think there are other kinds of meta expectations for other ones, but the ones I've talked about so far are they're domain independent, which is great. So we showed the benefit in 2 domains, but they're still module dependent, right? So this is still specific to explanation. And we might have another example where we always expect our planning component can generate a plan, right? So I would say if I can't generate a plan to achieve a goal, maybe that's a cognitive level problem. But having an expectation like the one I just described, that's also module dependent. And so what I think is a really interesting area for future work is, could we learn meta expectations? And so this kind of goes back to that vision in the future where if we could have someone who designs a cognitive agent, they might add their own modules, right? So James, in his previous talk, he added some rebellion modules. How could we have meta expectations for custom modules? Is that even possible? What would that look like? Perhaps we could learn them. And so just summarizing what I've talked about, metacognition is one of the core architectural commitments for MIDCA. I would like us all to think about, what do we think the architectural commitment should be? And so I showed some results in 2 domains for a metacognitive expectation for explanation. And for future work, could we learn meta expectations and also just building more metacognitive capabilities? So thank you. So that ends my talk. And we haven't really been doing questions because we've been kind of tight. And we're already kind of leading into the coffee break. So I guess if you have any questions, write them down. And I'm going to go back to our schedule here. Right, so we're just now wrapping up. Okay. So I hope you're seeing the schedule on the YouTube Live. It looks like we are about 10 minutes behind. So let's actually. So we're poised to start at 5:55 p.m. with Ryan Green after the coffee break. It is 5:43 right now. So why don't we extend the coffee break by 5 minutes? So Ryan, if hopefully you're hearing me, we will start with you at 6 p.m. Our time, which would be 9:30 a.m. your time. So we're now going to put the live stream on hold. Please feel free to put any questions in the YouTube chat, and we will see them. Thank you. Oh. Hey, Ryan. Are you there?
Yep, I'm here.
Okay, great. So I'm just gonna transition to giving you the screen. Don't feel like you still have a minute or 2 minutes, but I'm just gonna change things to make you the presenter right now.
And with a bit of luck, you should see the first slide of the presentation.
We do see that, yeah.
Yep.
Oh, I'm sorry. Whoops. Okay. So I'm gonna turn my video off, and just wait a minute or so before you start.
No worries.
Okay.
Yeah.
I was just looking at what. Not really any other titles in there.
No, I had a look this morning to see if we updated. But, need to have been. And I only printed that out yesterday.
Hey, Ryan. Whenever you're ready, you can start.
Okay, so we're aiming for about 20 minutes, including questions.
Yeah, that's right. You have 20 minutes.
All right, I'll try and hit that mark then, and
Okay.
I'll start.
We have a
now.
little buffer.
Okay. All right. Well, my talk is about metacognition for power management in autonomous systems. It's a bit more applied than theoretical in comparison to the other talks today. The model that we're working with is a undersea drone, which requires some serious power management capabilities. So I'll start off just by referring to the reasoning. So the reasoning for this talk and why we want power management is the undersea drones that we're working with are intended on going on extremely long missions, maybe months at a time. So this is an extremely power sensitive sort of vehicle that we're working with. And when it's undersea, it doesn't really have solar panels. So current power management solutions for microprocessors were designed for laptop and desktop environments, and not really that applicable to these autonomous systems. And also power management provides a starting point for more advanced metacognition services. So this is a way of getting the metacognition into the autonomous agent and providing that framework, which can then have other capabilities added in. So the current power management system in chips is called dynamic frequency scaling, or it's dominated by dynamic frequency scaling, which is the system which decides when to upscale or turn on cores the laptop or desktop CPUs. It functions on what's called an activity factor, which represents the average amount of switching done by the transistors on the chip. Now, in an autonomous system, we're really going to want to max out the CPU resources all the time. Even when we've got good plans, we really want to be on the lookout for any sort of unexpected events. We want to be optimizing those plans. We just want to be crunching numbers all the time to make sure that we're doing the absolute best. And this doesn't really gel very well with dynamic frequency scaling. So the existing power management systems will just be running the CPU at full power all the time, and that's not going to do any good for our power management and our battery life. So we decided to look into other alternatives. And just for our reference, the hardware that I'm referring to in this talk, although it's not completely restrained to this hardware, is the NVIDIA Jetson TX2. The TX1 is also extremely similar, so that will work the same. It's a quad-core ARM board. In the picture there, that's the development version. It's got 8 gigs of RAM. The TX1 has 4. And for an operating system, we'd be considering to use any sort of minimal Linux distribution. Doesn't really matter. Similar. And Moose IVP for the middleware, which doesn't come into it too much, but it does provide options for inter-process communication. So just briefly, when is the metacognition power management required above and beyond the dynamic frequency scaling? So low battery states is a good one. For example, if the battery is running extremely low and we are a distance away from our rendezvous point, we're going to want to really keep our decision-making narrowed to getting home. We're going to want to leave as much off, and we're not going to really want to ramp up the amount of processing power and drain the battery. Even if something interesting happens, we really want to keep on track and make sure we get home. Alternatively, we've got periods of low computational needs. We've got our plans sorted. We're just traversing the ocean for maybe days or weeks on end. And we don't want to be using up all of our battery power, really refining our plan or being extra alert for any unexpected events. And on the flip side, we've got periods of high computational needs. These are times when maybe a couple of unexpected events have occurred at the same time as we were replanning. And we really want to give all power to the CPU and the autonomy agent at once. Now, our capabilities, what does the metacognitive loop actually have access to modify the power draw of the autonomy agent? Primarily, it can modify the active core count in the TX2 reference board I'm using. That's got 4 chips with which it can set its core count from 1 to 4. It can set its core clock frequency. So it can scale the amount of power going to the chip to increase its gigahertz. And it can modify its GPU, which is a reasonable portion of the TX2. It can restrict to a low power core only. That's something that's fairly special in the TX2, but is becoming more common. and it can switch off external I/O ports such as HDMI. Now, that's something that we really have to deal with on commodity boards. Specialist hardware, that wouldn't be an issue, but commodity boards are perfectly fine for the job. We just have to make some considerations. And lastly, fan control. We wouldn't be expecting to use a fan control in undersea operations, but if it's a surface or a ground vessel, you're most likely going to be running a fan. And configuring the speed of that will extend your battery life. So on the actual practical side, how do we switch those CPU cores on and off and modify their frequency from our program? So using a Linux distribution, we can merely send variables to paths in the Linux file. The first step is to send user space to the scaling governor. This just switches the device from an automatic power management system, which I've already explained is not very applicable for a autonomy agent. So it switches it over to manual control, or in reality, it's switching it over to automatic control, but it's controlled by the metacognitive loop rather than the system's inbuilt power scaling, which has no comprehension of the actual use that we're using the CPU for. To actually send the message to send to set a CPU core to either on or off, we send zeros and ones to the online path as well. Continue on a little bit more, we can get a dynamic list of CPU clock frequencies by interrogating the scaling current frequencies. And we can then use that numbers from the list of numbers that gets returned and set the CPU frequency by sending that number to the scaling max frequency file path. Now the TX2 has a low power core. This is extremely relevant for these sort of long duration undersea sort of missions. And to enable this, we just simply switch cores 1, 2, and 3 off. Core 0 has the capability to switch into an extremely low power mode, which has a 51 kilohertz minimum speed. So that's what we'd really want to have, just to keep an eye on our sensors, make sure nothing unexpected happens when traversing for days or weeks at a time. Now, the capabilities that are not available, things that draw power that we're not actually able to modify. It'd be great to disable portions of RAM when they're not in use, but that can't be done. Sensor power management, such as GPS or sonar. These are big power draws, but as the metacognitive loop, you could take two approaches here and either have a metacognitive loop that has complete and utter vision of the cognitive loop and has a whole lot of code and is a very complex metacognitive loop, but that then controls power to the GPS and sensors. But I think it's far more rational to control the power to GPS and sensors as part of the resource management in the cognitive loop. And lastly, the actuator resource management. So that falls under the same umbrella as sensor power management, in that it's really only the cognitive loop that knows the best resource management for that. And adding that capability into the metacognitive loop is really duplicating resources here. So to touch on interprocess communication, what's the easiest way to communicate between the cognitive loop and the metacognitive loop? So in this extremely low power sort of environment, we want something that is simple to implement in code and once again doesn't really use any low level kernel calls that might actually chew up some clock cycles there. So a named pipe is quite a good option. It's straightforward to implement in code, very little extra code that may result in bugs, has very low computational overhead, and no file system access, which falls into that Linux kernel that before. The only real downside is it's unidirectional. That requires the cognitive process will need to subscribe to a separate pipe to receive messages back. But in most cases, for power management, that won't be necessary. Now, the other options, just to quickly cover them, are to use files for process synchronization. This does require calls to the kernel's API, which of course adds more CPU usage. So that's not a good option. We've got more advanced versions of inter-process messaging, such as sysv, provides a lot more capabilities, but once again creates overhead, and we don't actually need a whole lot of intensive communications to enable a power management process. Next up, we've got an autonomous pipe, which is also a good option. It does require each process to have access to the handle for the pipe, which of course requires something like a calling function that forks off both the metacognitive and the cognitive processes. And lastly, shared memory. It's also a very good option, requires semaphores, but you're not doing any sort of file system accesses. You're not creating any more required clock cycles. And so if you're linking your metacognitive loop to your cognitive loop using shared memory, that's a perfectly fine way of communicating that information back and forth for this purpose. So next up, the power management policies. So what actual approach should the metacognitive loop be taking to rationing out the power to the CPU in response to the signals it gets from the cognitive loop? And the two main approaches here are the absolute simplest, which is to maintain a constant iterative rate. That is to keep a watch on how long it takes for the cognitive loop to perform an entire loop through the MIDCA loop, and vary the CPU power up and down to maintain a constant rate. And secondly, to control a variable iteration rate, that requires a bit more communication between the cognitive loop and the metacognitive loop, but provides some benefits I'll cover shortly. So just quickly, the constant iteration rate turns on power if it notices that the MIDCA loop is taking longer than it used to, and it turns off power if it finds that the MIDCA loop is taking less time than it used to. It's pretty much that simple. The benefits are it's extremely simple. The desired rate can be determined in a number of ways depending on the complexity of the domain and the optimization of the cognitive loop. Scales well with new hardware, very little work to move to new hardware or different planners, and it works with pretty much any sort of cognitive loop or any components in that cognitive loop. Downsides, it does not respond to dynamically changing needs. So it's going to give your system a very, very good overall performance that's hardware independent. But on the downside, when your system could really benefit from some higher level, some faster thinking, or when it's really reversing those long haul sort of trips, it's not going to be hitting the maximum optimization for the power management there. And the desired iteration rate must also be decided before the mission starts, which makes it a little bit difficult, but not in complete end goal there. So, sorry, the variable iteration rate. Now this responds to the state of the cognitive loop and varies the desired iteration rate while in the field. So it requires a little bit more communication from the cognitive loop above the length of time that the MIDCA loop took to actually process. It requires some more information along the lines of how many goals don't have plans for them, how efficient the cognitive loop thinks the current plan is, how many unexpected events are currently occurring, basically an all-round stress sort of variable, the amount of stress that the cognitive loop is currently under. And it uses this stress variable to provide more resources and increase the iteration rate when under stress and decrease it when not. So this allows the dynamic power allocation for those situations where faster computational time is actually going to be needed. Now, its downsides, when compared to the constant iteration rate, is that it requires a larger amount of communication between the cognitive loop and the metacognitive loop. That requires a bit of work to be done in the cognitive loop to implement this stress variable. And even a basic stress variable is really going to be quite beneficial here, in that it's going to allow the variable iteration rate metacognitive loop to provide power when necessary. And a more complex stress variable is, of course, going to be beneficial, but you're going to see quite a lot of benefit just from a basic stress variable. So just to sort of round up with the discussion here, the reason that we would put this in a metacognitive loop rather than a cognitive loop is mainly because this allows the people running the cognitive loop to focus purely on providing the absolute best cognitive service, completely absent of any knowledge of the hardware it's running on, and leaves the metacognitive loop to actually provide the power to the cognitive loop. And at the lowest level, a constant iterative rate will work with most planners, but a variable iterative rate with a stress variable being communicated to the metacognitive loop is far more desirable. And when sort of taking this sort of power management approach, pay attention to the other processes running on the system. Even the minimal Linux environments are often can often be cut down a little bit further for these incredibly power-intensive scenarios. And there's quite often a bit more that can be hacked and slashed out of the kernel. And that is the lot. Thank you.
Thank you, Ryan. That was great. It was really cool to see an applied problem and learn about that. We're gonna transition now. So I guess we'll just hold questions till the discussion period. So if you have any questions for Ryan, just write them down. We're gonna go ahead and transition over to Sampath. Okay. Going to share the screen. Oops. Okay. All right. Okay, I believe we are good. So I'm going to pass this over to Sampath, who's going to talk to us about Baxter Robot with MIDCA.
Thanks, Justin. Hello everyone. I'm Sampath, and I'm going to talk about how a robot can interface with MIDCA. More specifically, what is interface with MIDCA. I'm going to show you it. Now let's get started. Everybody here had talked a lot about the cognitive architecture MIDCA, so I'm not going deep into the architecture and I'm not going to talk about it. But what I'm going to do is show MIDCA in action, applied to the blocks world domain through Baxter Robot. Whoever who don't know what a Baxter Robot is, I'm going to introduce it to you and talk a few things about ROS, and finally show you what Baxter Robot can do in a blocks world domain with ROS. So let's get started on the abstraction of how a robot can interface with MIDCA. let's get this image. So this is the bottom part of which is MIDCA. It's going to interface it through to the robot through ROS, and these are the ROS buffers which instantiate the communication. And here goes a simulator uh, for whoever who doesn't have a Baxter robot or a kind of robot of its kind. We can use the simulator. So let's see what a Baxter robot is. Baxter robot is manufactured by Rethink Robotics. It's mainly used in manufacturing industries, and there are different kinds of Baxter robot. The one which we use is a research robot, and it contains a screen and 3 cameras, one on the right hand, one on the left hand, and one on its screen. And moreover, it contains 7 Baxter's arms contains 7 degrees of freedom, and the sonar ring on its top is actually to detect the objects of its size. So what are we expecting from Baxter and MIDCA? Should perceive the world, detect objects, understand the speech from the human, and infer goals from it, create, plan, and execute it. Let's look at ROS and then get deep into how Baxter with MIDCA does. So ROS, Robot Operating System. Don't be deceived by the word operating system. It's ROS is not an actual operating system, but it contains software libraries which can be used to build a robotic applications. So it's a robotic middleware. So let me just introduce to the concepts of 2 ROS node and ROS topic. Uh, they can come in handy for my next slides. So what a ROS node is, consider it as an executable application, and a ROS topic is a communication between ROS nodes. So let's go deep in what MIDCA has, what MIDCA and ROS interface has. So we have an object detection node where object detection is performed. I mean, it recognizes objects and gives the real world coordinates of it. And the voice recognition node where we speech to text, and then we consider whole MIDCA as a node. And the Baxter grabbing node, which are the end effector functions to raise the arm, to get to the location and such things. Let's see how communication goes between these nodes. We have the object detection nodes, and here the object underscore position is a topic. So what the object detection node does is it recognizes the objects and gets the real world coordinates and sends it to the MIDCA. And similarly, the voice recognition node uh, from the human, I mean, transforms it into the text and then sends it to the MIDCA. While MIDCA does a lot of things, it perceives the state, I mean, interprets the goal, and then plans, executes, and then gives the end effect or the task. Similar to going to certain location, I mean, grabbing the object, raising its hand, releasing, similar kind of things. And the MIDCA feedback is actually a topic which contains whether the action is done or not. Yeah. So let's see how MIDCA handles all these topics. So we have this concept of handlers in MIDCA. What they does, I mean, they asynchronously communicate uh, with ROS. I mean, they synchronously communicate with ROS, gets the messages from those object detection nodes and the voice recognition nodes. So we have 3 kinds of handlers here: object location handler, utterance handler, and feedback handler. So object location handler gets the real world coordinates of an object, and then during the perceive phase, those from those coordinates we actually get the predicates, and during the perceive phase they are actually given a states. I mean, the states are updated. And for the utterance handler, we get the text representation of it, and during the interpret phase we infer goals from that text, and the feedback handler is to get the whether the action is done or not, and it's done during act phase. So what we have for the experiment, so we have 3 to 4 different colored blocks. We have the Baxter robot, and I'd like to talk about 2 different functionality apart from MIDCA, which we have done here in order to get going. So the one which is speech to text, and the other one is object detection. So let's get started with speech to text. We use Pocket Sphinx to train the model on a set of different utterances, and then we convert into the predicate format in the interpret phase. So suppose if you have an example of stack the blue block on the red block, so they were converted into on of blue underscore block comma red underscore block in the interpret phase. And in the object detection, so we have used Asus Extion Pro 3D live camera, which is a depth camera, in order to detect the objects. Though the Baxter has three cameras, we choose to use the depth camera in order to get the XYZ coordinates, because from a 2D camera we could only get XY coordinates. So what we have done a whole lot of things here. So in order to detect the blocks which you have, which you can see blue, red, and green, so we have done different tasks in order to get that. So firstly, the filtering. As you can see in the diagram here, you can see the whole lot of room space. So we just limited it to the table and the blocks. And downsample the pixels. This is done because to improve the efficiency in calculations in the computations. So, and then identifying the plane and then removing the plane from the picture. And finally identifying the blocks based on their color. So that's what it goes into. This finally, let's look at the video. So we can connect. Oh. Oh. Yeah. Uh, in 9W. Oh, okay. Oh, I guess it should play. Oh, okay. Okay, that's. I probably, I mean, keep it online so that everybody could view that.
Yeah, we can add it.
Yeah, we can add it. Can add that later. So, yeah, it's a video of Baxter in the Bloxwell domain. Given a speech, given a speech, it stacks the blue block on the red block. It can stack up to 3 high. So, so I'm going to conclude this and future ideas. So, so abstraction, we can actually interface a robot with MIDCA. It's not just limited to the Baxter robot. Any robot of its kind, like a turtle sailboat or something like that. And we also have a simulator, and through the simulator, if it doesn't have a physical robot, we could also work on it through a simulator. So what are our future ideas? So Baxter robot to be doing in a blocks world domain, but then we would also want to expand it to setting the table for a restaurant, or making it work when 2 or more blocks of same color exist. So those are my future ideas. Yep. And that's it. Thank you.
Thank you, Sampath. So in his presentation, we will add that online later. So actually, we'll make a lot of the videos, all these videos available. So if you check in back later at the URL of the second MIDCA workshop, and we'll post it in the comments here. We'll post videos and other content later in a week or so. So now we're going to transition to our next speaker, Zora Dannenhauer, and she's going to be talking about goal monitors, acting, and perception. And here she is.
Hello, everyone. I'm Zora. I'm talking about goal monitors today and the relationship between interpret, plan, act, and perceive. This is MIDCA architecture, just a cognition phase, as you saw in other talks today. I just want to mention that MIDCA has 6 different phases, and my work focuses on these 4 phases: perceive, interpret, plan, and act, and the relationship between them. And I will explain how interaction between these 4 these phases help the agent to accomplish a task successfully in a word. My research plan focuses on how an agent can respond appropriately to a dynamic word. A dynamic word is when the changes might happen in result of other external events, and that can affect the agent's goal and tasks. Last year, we reported integration of planning and perception using plan monitors. Plan monitors guide vision to focus on features that only affects the plan. And if any changes happen to those features, then a plan refinement will be done in response. But replanning or plan refinement is not only the solution for the problem. Sometimes the agents need to alter its own goal to be able to successful. So we use goal monitor here to focus on changes that affect the agent's goal, and these goal monitors track that the goal maintain its usefulness, and we'll see if it needs to pursue the goal. In plan phase, planning begins to find a sequence of actions to accomplish the selected goal. Plan monitors are generated during the plan phase, and they focus vision to only monitor the features that affect the plan. And if the perceived state differ from the expected state, which is the preconditions of the operator, which if they differ, then it leads to plan refinement or replanning. Then the act phase begins with when the planner finds a valid plan in the current state. And so this is part of the future work. We're gonna use the plan monitors during the execution part to see if the condition of operator are different from the agent expectation, then it results in replanning and plan refinements too. And then monitors observing the conditions of the goal, and if those conditions are not valid in the states, then it leads to goal transformation or goal abandonment. A goal reasoning agent has an explicit representation of goals. It is able to formulate their own. They are able to formulate their own goals. As Mike said before, they are so MIDCA is not waiting for the person to tell what goal to choose. It can reason about its own. It can reason about and generate their own goals. So there are two different ways in MIDCA that can formulate the goals. First, there are some rules, and each are some conditions, and if they are valid, then a goal is generated. The second part is a discrepancy happen. The agent's expectation is different from the perceived board. So it detects a problem and it tries to explain it. And based on those explanation, it formulates the goal to remove the cause of the problem. So and a goal, and then these agents are able to manage their own goals and select which goals to pursue. There are some cognitive architecture like Icarus that use rules to generate goals, and so in this kind of methods, the current condition trigger what goal to select. And some other approaches like I guess PUG use numeric utilities associated with symbolic goals, and they generate dynamic utility, and that's how they select their goals. And another example is MR2 that using domain-independent motivation way to select goals. So we say that the reason to select or formulate goal should be monitored, and also the reason that affect the goal selection, if you monitor them, it helps us the goal selection too. We categorize our goal monitors to operator side and explanatory. The operator style, when the goal is generated based on some rules, so we observe the preconditions of the goals, and if any change happens to those preconditions, the agents decide to transfer the goal or abandon the goal. Explanatory is when the second type, when goal is formulated based on explanation, and then this goal monitor observes the causal justification, and if anything, if the reason changes, then it abandon the goal. So in MIDCA, interpret and when it adds a goal to the set of pending goals, it create monitors for the reason that it lets the agent to choose that goal, and these monitors will specify what to monitor in the state, and then if any change happened to them, then the monitor fires and it remove the goal from the set of goals, and also if in the middle of planning, it notify the planner too, and the planner doesn't need to generate a plan for that specific goal. Here, a piece of code that I put here that it explained when the preconditions of a goal is not satisfied in the state, then it results in dropping the goal. This is an interpret phase in MIDCA. You don't need to read the details here. So just want to say in the first part, it checks to see if any monitor fires, and if it does, it abandons the goal, and it removes the goal from the set of goals it has, jihad, as you can see here. And when it formulates a goal, then it creates goal monitors for that specific goal. This is an example for operator style. Here you can see that this is our goal. This is the goal operator that we have, and the preconditions is a package exists in a warehouse, and an order exists for that package, and if they are met in this state, then a delivery goal will be generated to deliver the package to the destination. And we monitor those conditions, that an object exists in the warehouse and an order exists in the warehouse. See here, this is an example that the package P1 that has to deliver to D1, and this package exists in the warehouse, and this goal is generated. But when package 1 is stolen, then interpret will the goal monitors will remove that goal from the set of pending goals. We ran this experiment in logistics domain. The initial state is we have n warehouse and 5 packages in each, and 1 order exists for each package. The x is the number of warehouses, and y is the performance, how many goals is achieved by MIDCA. As you can see, the MIDCA with goal monitors has a better performance than MIDCA with no goal monitors. For example, when we have 10 packages, and oh, I forgot to say that during runtime, six packages from different warehouses become lost. So here, goal monitors can detect the changes and remove the related goal from G. So here, as you can see, when the number of warehouses is 10, the number of goal achieved is only 20, because only four warehouses will be achieved, and is less than MIDCA with goal monitors. Show that the integration of interpretation, planning, and acting in a cognitive architecture MIDCA, and as we saw, using goal monitors increases the number of goal achieved. The future will be, as I mentioned, we want to use the plan monitors in execution, and also when a monitor fires, the agent should reason about it, and because sometimes it reason about it to see if it needs to respond to that change or not. And also explanatory goal monitors, we need to work on that. Is still in the the preliminary base, so it's just like the first steps on that. So we need to explore that part. And also, we want to use these goal monitors in human-robot interaction. When a human asks a robot to do something, the robot needs to know why, and based on that, and monitor that reason to be able to if it needs to pursue the goal later or not. And also, when a goal monitor fires, the agent needs to decide to abandon the goal or transfer. For now, we simply drop the goal, but later we wanna reason about it and see in which conditions the goal needs to be abandoned or need to transfer to another goal.
Thank you, Zora, for your talk. So this is the last talk of this session. So what we have coming up next is, ignore this message about the coffee break on the slide. To now take our coffee break. We're a little early, actually, from the schedule that was posted online. We're about on time. So we're going to take a coffee break until 7 p.m. So please come back and join us. And then at 7 p.m., we will have a discussion. So basically, we're going to be talking about what we've found interesting from some of the talks, actions we want to take MIDCA, do we have new ideas? Ryan's talk and James' talks both added some new content. These are from the groups that are didn't participate last year and have started using MIDCA, and so I think there'll be a lot of interesting discussions. So feel free to join if you're interested in joining the Google Hangouts. So Ryan will be on the Google Hangouts with us. If you're interested and you're watching the YouTube Live, just comment and we can send you a Hangouts link to talk. And so we are now on a coffee break, and we will be back at 7 p.m. That's a great point. I will. Yeah, I'll post the link. Okay. Hey, Ryan and Martin, are you guys there?
There has been
yeah,
another guy, Chris Novak, with us. He's stepped out for the break. He should be back. But anyway, we're still here and we can hear.
Can you hear us? That microphone should be on. Yeah, it's registering. Oh, sure. I'm just going to go respond to David's email.
Well, they've already left for the day, so.
Oh, well, that doesn't matter. He'll get it tomorrow morning. Oh, yeah, I suppose if it doesn't matter what time, I'll do it afterwards.
Yeah.
I'm just going to mute us again so we're not
So that whole, hello, can you hear me now? So the whole spiel was lost on the slides. I can skip the slides, but why don't we just continue if everybody can hear me now? I was wanting to, so Dustin had just opened up with a mention of complicated domains for different people that use MIDCA in the community here or outside, that often what he was the main point he was making, or one of them, was that it's the domain that drives the cognitive functions that are necessary and what the research would then be looking at. And he mentioned Minecraft as being another complicated domain and how interesting that would be for incorporating into MIDCA. I was starting to say that the domain in the Gators project with underwater vehicles, surface vehicles, the marine world, moose, and that was also a very complicated one. Sravia is starting to look at moose. I was going to ask Ryan whether his experience with moose, I know that was a difficult interface to work with, but are you still have mixed feelings about how suitable that is for a domain for open research, or can you comment on your experience with moose and that kind of a domain?
Sure. So Moose is very similar to ROS for those who aren't familiar with it. It's designed for surface and underwater vehicles and is built by MIT. Its main selling points are that it's extremely low computational overhead when compared to a middleware like Moose. Like a middleware like ROS. So it's very simple, but at the base level, it works in exactly the same fashion in that you have a central process. In Moose, it's called MooseDB. In ROS, I can't remember the term now, but the central process through which all the nodes in ROS communicate. On Moose, it's called the MooseDB, and that's the central node in which all of the Moose programs, through which all the Moose programs communicate. So it's really the same. And if the question was more on the technical side, or whether the C domain are good domains, I'm not sure. Mike, could you just clarify on that?
Well, a little of both, but just getting at Moose itself too. For instance, Flavia got the example with the kayak. It's kind of like a little toy example that comes with the simulator and with Moose. She did get that working, but there's no real, pardon? One of the things that she had a question was like, there's no tutorials on it, and it is very complicated, and you have to kind of like figure out a lot of that on your own. So one question is, is there a tutorial? Yes, I am interested in the C domain itself, and in particular, though, we're also interested in feedback on Moose, or things to look out for is also of helpful. Maybe that's a offline conversation, but she had another comment. Shravya, why don't I let you speak it though?
Yeah, I just have the simple question, like, can Moose communicate with other applications rather than .moose files or .moose applications?
No. I mean, you could create an interface, but it's not designed to communicate with other applications. It's designed to run in its own little isolation on a craft out on the ocean. On the topic of tutorials and so forth, there is actually some resources available. I did have some trouble finding them myself, though, and sort of stumbled upon them after I'd already started. They are out there, and in addition to them, I'll send you a link if you want.
Yeah, sure. Thank you.
There's a large number of missions, example missions in there, which each have their own page describing what they're actually doing. And if you sort of work your way through, they increase in difficulty as you go along. You can sort of piece things together that way as well. So I'll email you that information, which should be helpful.
Sure.
Well, I also wanted to comment while we're at it on the domain, and not just the domain, I'm sorry, Ryan's presentation. And a number of them this year have been about what metacognition, how you can think about metacognition when you're in a domain. And the problem of power management, well, Martin mentioned that to me before, but until your presentation, it didn't dawn on me how that really is a metacognitive problem. And so I thought that raised a bunch of interesting questions when you had that the simple way you could do it versus the variable iteration and the trade-off there. It would be interesting to see if you can measure that trade-off, how there is extra overhead maybe for the variable rate. It seemed like you suggested where the simpler one, you had less overhead. And in fact, the overhead might cause more power drain trying to do the variable iteration. So there's maybe a sweet spot in certain kinds of problems or something. Can you comment on that?
You're still muted, Ryan. Sorry.
Sorry. I presented two of the main umbrella sort of approaches there. We should be receiving hardware in the next couple of weeks where I'll actually be able to start getting some metrics on the power draw of these processes. What I'm expecting is that the computational complexity of either process is going to be absolutely negligible compared to the iteration rate of the cognitive process itself. So I believe the variable is going to be by far the more desirable. So,
I actually just going off of that. Can you just mute yourself, Ryan? We just get a little feedback from it if you don't. Yeah, thank you. Yeah, thanks. That's great. So, Mike, that made me think about so talking about metacognition and power management. I haven't really been thinking about, so a lot of times we talk about resources in the world, but I haven't necessarily thought about resources at the cognitive level. So I almost wonder if power or energy is a resource that we might be able to think about mental actions consuming. So, maybe planning is a resource, like a resource heavy mental action, or where this might come into play actually is when we swap modules. So actually in the last MIDCA workshop, we had an example where the metacognition actually swaps in a different planner because the first planner was unable to achieve a goal. It's interesting, what if we swapped planners because one planner was less resource intensive? So I haven't really been thinking about resources at the cognitive level. So I that's really interesting, I think, for future work.
Yeah, actually, just to comment on that, the swapping out the planners for power management was actually one of the first places I went to. I came to the conclusion basically that having the cognitive loop try to decide how much planning is necessary, and having multiple planners seemed like a very difficult job to keep all those planners functioning, the code, well-written code maintained, so forth. So the path I took was instead to have one planner that does the best job and then give it more or less power depending on how much stress it's under. And a good planner, as I'm sure most people would agree with me, should not take the same amount of time for a simple problem that it does for a complex problem. So it should just find the shortest path. And whether that path is short or whether it's long depends on the actual problem itself. So one planner with hardware agnostic sort of capabilities is what I was going for.
Thanks, Ryan. That's interesting. Does anybody else have any things that you thought was interesting, or questions or anything? Or any of you want to take a stab at what you think an architectural commitment should be for MIDCA, or my slide?
Sure. Anybody? Well, I'm going to stay with Gators and some comments. So Martin's there, right? We have Martin. Okay, yeah. So I had promised you, Martin, in our last telecon, I had promised this example we had talked about that I was toying with, which was the mine clearance and the queue route and so forth. I actually did put together some on that and showed them to the students that are working on Gators. We talked about that, and I had told you I was going to send them to you. I've got really about 10 more minutes worth of work, but then I went on vacation. So expect that, and I don't know that that's anything that we're planning to do as is. I see it as a talking point, though, for how explanation might fit into some of the tasks that would be related to, because you had suggested that mine clearance might be one of the problems they look at actually with one of the Remus platforms if the deep ray glider wasn't ready in November. And anyhow, so this mine clearance amphibious kind of thing, I was going to send you the slides, some PowerPoint, and maybe we can then talk some more about that. But I would like to look for ways that explanation might be able to contribute, or it's at least have some synergy with what you guys are doing there in Adelaide. So
yeah, hi, Mike. Yeah, that is still the intention with Autonomous Warrior. The Deep Ray glider, or the Sunray, which is the prototype, won't be ready, but the DST Everly people in Sydney have more experience with mine countermeasures, and will be doing something at the exercise with that. So it might be possible to do something there, but certainly incorporating explanation into the things something that we're interested in longer term as well as in the short term.
also, I believe, let me see if we got this. Yes, can you hear me? Yep. Okay, so I also think that the problem of the battery, because you had mentioned it before in our last talk, that Ryan was looking at power management issues, and now I'm excited about it. So I think that is something, right? You expect maybe the power to be a certain level, but you've done more computation than what had been normal, and you have less power, and that might then be an anomaly for us, and we could have some explanation that would, in the GDA sense, trying to use our version of MIDCA, generate a goal to do something in the power management realm. But what would be helpful would be if you had a particular scenario that you're playing with, Ryan, or you guys have, that illustrate also the power at a high level, what would be occurring, like in terms of events in the scenario, and the branches that might happen. If it did one thing, this is what would happen if it did something else, and that just gives us kind of something to help us think about that in the same vein as what we were doing with this mine clearance problem. But so later on, I think I'm just asking, this is just to say I'm asking Ryan and you to, if you have an example scenario that's just in a text file that says this is an example, that would be that'd be useful for us.
There is no example in the text file at the moment. In the simulations, it's just running full power all the time, which is, it is possible because it is a simulation. But it's something that's been identified will be an issue. So that's what we've sort of, that's how we came up with the idea to make sure we had a plan in place for when this actually happens. The examples of when you want to really crunch numbers might be at the start of the mission. It's been given a bunch of goals. It's starting with a blank slate. It takes quite a bit of crunching to find plans to achieve all those goals, to order the plans, so forth. Once that's in place, it can then go to a lower stress mode, which then shuts down some cores, shuts down some of the CPU frequency. Because at that stage, it might just be refining the mission. It's got a workable mission. It's just seeing if it can come up with a better one. And that's not something that really needs to drain the battery for. So that's sort of the two different concepts that we're working with. Did you want to comment?
Yeah, this is being recorded. Oh, it is. Yeah. That's great. Okay. Well, so this has been really specific to Gator, so maybe we can broaden it to, or
you guys have any thoughts or anything that So right, okay, yeah, we're not really. I was kind of just asking if anybody here had any questions or comments or anything. I would just like to note, so I started working with James Boggs, who's doing the Rebel Agents with MIDCA about like 2 or 3 months ago. He was working with someone else at the Naval Research Lab who ended up taking another position, and so I'm working with him now. And first of all, I just want to say, for all of us using MIDCA, it's pretty exciting because he has a multi-agent setup and they communicate, which I believe is the first example of multi-agent MIDCA scenario. And I also just think Rebellion, so it's surprising how, so I did a brief survey of trying to find work on it, and there really has not been a lot of empirical experiments run with Rebellion, and Rebellion just seems so interesting and so useful because so many times humans, mess with robots, or they give a goal, but there's really some like the comic that Mike mentioned, like a goal or a task, your motives to it, or it might violate some ethics. And I think that's something so interesting. I mean, I think that's a great, so I'm interested in goal transformation, and I was talking to Stravia about all the goal operations and deciding when you should. Yeah, and Travi was talking about goal types and this stuff, and so I think that Rebellion is a great situation where you might want to do goal transformation, because suppose your own a robot has an owner and its owner tells it to do something, but it violates the ethical policy of the agent. The agent probably just shouldn't do nothing. It should probably do something. So some kind of goal reasoning to transform to maybe do a similar goal. Anyway, I just think this could give us a lot of context for at least myself and Stravia and those interested in working on this area of goal transformation and using goal operations. There could be some rich scenarios here, I think, for research.
Well, my comment to that too is, we had some evidence. We had talked about where does the reasoning about goals exist? Does it exist at the cognitive level or at the metacognitive level? And with us, I think, Stravia, you were on it as well, but it was your work mainly where you argued that that kind of an operation to change the goal kind of belong, because you're reasoning about goals and the benefits about it would belong at the metacognitive level. We had some evidence, but then there was a trade-off there, actually, and I don't know that it's clear. That's a big question, I think. James was using eval. I would think we argued about that over the first break, whether it might be actually not eval because we something else. But whether it's an interpret or even an intend, but reasoning about the goal might, because he did claim it's metacognitive too, reasoning about the goal. So we have a little bit of evidence from that paper, but that was, we kind of set it up to do it that way. We kind of knew what we were illustrating the trade-off. So a more hard look at, if you're going to reason about goals, there's different things to reason about goals that are given to you or goals that you generate or that you're selecting, and trying to make decisions about that. Is that metacognitive, or in what phase or what process be in charge of that? That's actually nobody really thinks hard about that, and there is no real you can't go to the literature and say, oh well, here these guys say that and they say this and I believe them.
I would like to comment on that. And so Mike, that's excellent. So I really like that work that we did, and I think it comes down to, so you talked about whether or not the trade-off between having goals having like goal reasoning happen or goal transformation happen at the metacognitive level versus the cognitive level. And so in the work that we did, we basically implemented a planner that would take a world state and a goal, and if it couldn't achieve that goal, it would actually just come up with a different plan that would technically achieve a slightly different goal, but the goal itself wasn't explicitly being reasoned about. So it was just within planning knowledge, the equivalent of goal transformation was happening. So and the example I'm talking about was, just to make it a little easier, is that there were two types of block towers that could be built, and one of them used a resource like cement in between, and another one didn't. It just set the blocks on top. So the original goal was to use cement, but if there wasn't any cement available, it would just stack the blocks. And so that's interesting, because the plan that was coming out wasn't achieving the original goal. But the most important thing, I think, is that I think in goal reason, I think we really do want to treat goals as like first class objects that we want to keep explicit and reason about. And I think if we're going to do that, I think it falls at the metacognitive layer, because a goal is a goal. Yeah. A goal is something internal. Even though a goal is a world state, it's something the agent has about the world state. So yeah, and this is where it gets a little tricky, whereas like, should it be meta or should it just be in the cognitive level? But I think I think this is the case. If you're going to change any knowledge that the agent has, or anything in memory that the agent has, that should generally be considered meta. And so because goal transformations are changing the agent's goals, it's an operation that's happening cognitive state. And yeah, that's right. Oh yeah.
I got excited here. I'm just taking and saying though that most of the AI, I mean the bulk of the AI community does do all of these things. In the goal reasoning community, very few of us have this meta layer and try to represent it that way. So they actually have code that is doing some reasoning there. So I have written when I was in Prodigy. I mean, I wrote things that would, in effect, reason about the goals, but it is a little slippery. And I also would say that, yeah, this is a strong cognitive point of view, right? There's the people, what is it? The situated cognition. People say everything is really in the world. And so did the behaviorists as well. But a good cognitivist would say we really, everything is in our head. We have representations of things in the world. We have things impinge, light waves impinge on the eyes, but we have images that our brain interprets, and we have memories of things. Everything is actually cognitive. And then we should be a philosopher, I guess. But it is important to, though, computationally and look empirically at what would be the benefit of doing it at one level versus the other, and examine that a little bit more rigorously.
So I don't want to like hog too much of the discussion if any of you want to jump in, but so just going off of this, I think that in just the work that we had done, where it was the goal reasoning, the goal transformation was happening inside the planner, you basically needed an expert to you needed that planning domain knowledge in there in terms of the operators. And that's why I think part of what I mentioned in my talk was this vision that like we could just in the future, when we have fully a lot more capabilities in MIDCA, you could design a cognitive agent. You specify what kind of cognitive modules you get and all that stuff, and then you can get a bunch of things for free. And one of the things you could get for free is if you specify kind of a ontology of goals, or all the different kinds of goals, or maybe it's just an ontology of world states, and from there you infer possible goals. But you could have general search mechanisms that decide if at any point in time, if any goal is unachievable, B. And that seems to fit in the metacognitive, and because it's explicit and goals are objects that we can change and operate, then I think we can get general capability that can apply.
I just want to say, when you want to decide which goal is achievable is based on the states in the world, right? So I don't know.
Yeah, right. So right. And so this is this is a great point. I think so even though the meta level is concerned with the cognitive level and the cognitive level is concerned with the world, you can't get away from the world in the meta level. And you could argue that technically inside, because in MIDCA's memory, there's an internal world state. So MIDCA's perceiving the world, but it has its own, like in its memory, it has its own state of the world. It's actually not the state of the world. The state of the world is like its own grounded thing that we get something that resembles it through perception. And metacognition, I don't think is going to be able to get away from that. It's going to have to use, like you're going to have to know real values of what's in the world at any point in state to do these things, like to know that a goal is unachievable. But I don't think that's necessarily a problem. Yeah. Ryan and Martin, and do you guys have any discussion items? Anything? Any comments or questions you had?
Yeah. Hi, it's Martin here. I mentioned the Dustin in the break, but most of the rest of you probably wouldn't be aware. We've also had a third colleague of ours and friend, Chris Novak. Yeah, so I don't have any questions as such, but I was going to make a comment about James's talk, and I guess you've already covered some of that. But I also thought it was interesting, the idea of rebellious agents. We heard David Ahar talk a bit about that when he was here back in September after the IDCA conference. But Chris is starting to look at representations for legal and ethical issues, because in the military, apart from the ethical issues which you've already discussed, and they don't have to be in the military domain or the defence domain, there's also things like the law of armed conflict and other legal requirements that agents would be, or or capabilities would be required to observe. So I don't think we've, or even Chris has necessarily thought about how some of these things could be implemented, but the idea of the rebellious agents maybe having, well, keeping a focus on what's going on and having the ability to intervene on the more standard processing might be an interesting thing to continue to pursue.
Yeah, so related to that too, and certainly the ethical questions I have not tackled before, but that would relate to when you're reasoning about a goal. And James argued for that, though there are some distinctions that came to me when his didn't have a chance to raise. I believe I talked with Zora about them over one of the breaks. So I could imagine if my superior ordered in during wartime, there are rules, as you suggest, about what is legal, what's ethical, and soldiers, if they're ordered to shoot a civilian, can refuse an order. You know, they're supposed to not argue about orders and just do that. But I think there are cases where rules about that. So if I had the goal given to me, shoot a civilian, well, I should be the rebel, and maybe I can cite Geneva Accords or something that is kind of clear. But he was talking about also where I have the orders to defend myself when people are shooting at me or shoot the enemy or whatever. And those rules, that's but so the point I want to make is, though, the reasoning about the casualties when there's civilians that would have side effect, now you're also reasoning about the plans and the execution of the plans as well as the goals. So it deals with planning and not just reasoning about the goals. So there is, what is planning versus what is the goal reasoning, or for a rebel agent. I think that is often we easily can mix the two. And so actions have effects, and we need to think about that. But goals don't have actions yet till you do the planning. Now, you may know about arguments of predicates when it's if it's going to be, I said shoot, but it was when the goal is to have destroyed the enemy military, armed forces, versus to destroy the civilian. So that is the goal. That's the reasoning about the goal. It's and the goal arguments. But then when it's starting to think about the side effects of the plans that achieve the goals, then there's actually more to it, and there's a little distinction there that is important, whether ethics are involved or not.
I just want to say that's really interesting, Mike. So most of the time, goals tend to be subsets of world states, and it's interesting. I don't know. I feel like in the goal reasoning, I haven't heard much of, or
put a block on the red block, and then it's a variable. It's not a concrete one, so it can be variabilized.
Okay, Mike just made a comment that they can be variabilized, so kind of like lifted states or something. Yeah, not grounded. But I just mean, so and actually, yeah. So a lot of times when we specify a goal, oftentimes there's the state is much bigger, and there's just one. So like even with the Baxter and the blocks, there are like 4 or 5 blocks on the table, and you give it a goal to stack 2 of them. But the goal doesn't say anything about the other ones, but maybe you have ethical policy, and it's just really interesting that there's, so like in James' example, like what you were saying, right? So to reach the goal, a civilian would be killed, but that's not specified anywhere. So it's almost like you need an inference. Yeah. Right, about the plan. Right.
I was just starting to, I get excited here, right? So I was starting to say, though, you can put costs to actions. And if you want a cheaper plan and you just give certain actions like to harm a civilian has a higher cost, including a legal cost or ethical cost, your conscience, maybe if you're, but I don't, forget that. Anyhow, there's a cost and you want to minimize the cost. You want to choose ones that allow it, or there's other ways. And then it's part of the planning operator knowledge. And it's a planning problem. Or you can solve it that way too. It'd be interesting to see how much you can do at the goal, because I could have certain information about goal types. As Robbie was talking about goal types, we haven't really started using an ontology for the predicates and classes, but there could be certain goals, like destroying something is a different type than on or next to, where I'm in a different class of a goal, and I could learn that certain kinds of goals, the plans associated with them just tend to be costly or negative or have an ethical implication without having to do the planning yet. And I could kind of have associations with goals without, to avoid having to do the planning. So there is, a bunch of good things.
Yeah, I just want to say, so I sometimes forget how intimately connected plans are to goals. And you can imagine an agent that has a lot of pending goals, and as it's moving around in the environment, the amount of actions they need to take the goal would be changing. So it's almost like if you had a bunch of goals, you would constantly want to be monitoring how much effort it's going to be able to take to achieve those goals. But then you might be doing just so much unnecessary planning, and just linking those. I think that's an important thing to consider in doing goal reasoning is what kind of plan is going to take me from the current state, and if that leads to like opportunities, right? So if all of a sudden it's very easy to achieve a goal, maybe that increases its priority. And I don't know, we don't have anything right now that, no. Yeah. Mike said that was an interesting statement. Which the opportunities?
That it changes the opportunities for goal selection as you're doing planning. Well, I haven't thought
of that. Yeah. Well, we are around 7:45 or 7:46 here, which means it's probably like 11:15 a.m. Adelaide time. Yep. So we're kind of in towards the closing. If you guys want to say something, or
yeah, I was just going to make a comment about the quality of the visually, that is, of the presentations this year as opposed to last year. It's viewing things remotely. It's actually been a lot better. There have been some issues with Prezi, and you've probably experienced those too. So that didn't quite work so well. But this year, the content on the slides was really, really clear, and the sound quality was a whole lot better on generally. Yeah, so well done, and thanks for organising it, Dustin.
Thank you.
That's great. That's great to know. So this is our first time having remote speakers and also having speakers from the other side of the planet. So, which is great. So yeah.
Okay, so this is more because I know that we're finishing up here, but I wanted to just kind of let the Australians, the Aussies, know as well as some of the others here that work on the periphery of there. We actually have some people here today that work on different projects that aren't MIDCA, but I did get to talk about how there is some intersections here that may or may not be as apparent, but there's some interesting work that's starting to happen because we've done, and Sravia kind of mentioned it, that some of the goal operations that we do, like goal selection was done in the intend phase in her master's thesis, kind of looked at that in isolation and assumed that goal formulation wasn't happening at the same time and that these other goal operations, goal change didn't happen at the same time. It was just selection, and you studied that in kind of isolation. And now we're starting to look at, well, what do you do if you had the choice of, you got to pick, you have 10 goals and I got to choose some, or I could change the goal, maybe if I can't do them all, or there's, new goals coming up. How does that change my selection problem? And you just mentioned right now, as I plan for a certain goal, things may become, all of a sudden, the world changes that makes opportunities that I may want to take advantage of, or opportunities to do some goals I'm not currently working on, or so it gets complicated. But so this, and goal monitoring as well. So I've got 3 students that are now starting to do things that relate to different goal operations, and their work is starting to integrate, and the issues are overlapping, where there's going to be some, I'm excited about it. I think there's going to be some interesting possibilities that will arise. Well, we'll see how it plays out, but the kind of reasons that you have to achieving a goal, you want to monitor, but those reasons comes from explanations. So Zora's doing the monitoring. Explanation is starting to be done by Sampath, but those explanations can help with formulation. The whole selection task can be, I think, also informed by causal explanation, and you actually might metacognitively want to reason about what would be a simpler task, because I can't think about this forever, or I'm going to run out of battery juice, right? Or I'm going to run out of time. Time itself is a resource. Now, I don't know that we'll solve everything happening at the same time, but at least pairwise, we're going to start to look at some of the operations. If you have choices that happen pairwise at the same time, now what do you do? And I have high expectations that I hope my observations of their research will sync and will be a positive surprise. Okay.
Thanks, Mike. So yeah, I'm just gonna wrap it up. I'm just gonna make a few comments. Before I do, is there anything to Ryan and Martin and Chris? Do any of you want to make any last comments or anything, or anything? No. Yeah, Shavia.
I just had this simple comment, like uh, we are like when I was talking with Dustin, we were talking about the domains, and he was talking about the Minecraft domain and another video game domain which he wants to integrate onto the MIDCA. So I would like to add this, that instead of building newer domains to do our tasks, like Dustin has implemented expectations in Beacon domain, and I have implemented the selection in construction and restaurant domain. So I think that rather than building different domains for our different tasks, we should try to implement all of our tasks into a single domain, which is kind of generic. That might help the to be more faster pace or something. Yeah. Uh-huh.
Yeah. This is a great comment, Stravia. I think that to really do great goal reasoning research, we need rich domains. We need like a large variety of goals, and that's where you get really interesting behavior. And I think that's one place goal reasoning will shine. So I definitely am in agreement with that. And so I just want to say thank you so much for everyone joining us for this. The talks were great. I learned a lot, and I hope you all enjoyed them. And so what's great, and so I feel like we definitely met our objectives for this workshop. We brought in, we got to hear from the folks from Australia, Ryan and Martin and Chris, and James about Rebel Agents from New York. So it's so cool to see some outside groups using MIDCA. And and so I've kind of transitioned to the Naval Research Lab in Washington, and so now I'm kind of an outside group from the original core hub of MIDCA. And so I just before we go, I want to take kind of another shameless plug that please feel free to update the website, and also please feel free. It's an open source project. If you see some code that you're like, that could probably be modified to be a little better, do it. You can do it. You have the freedom. So I'm motivating. If any of you are ever bored and you're like, oh, I just want to do some coding, go on MIDCA and look through some files, and I'm sure you'll find something you think you could improve. So that's and also just remember, if MIDCA becomes better and more popular, more robust, we all get more citations. So yeah, so I just want to say thank you all, and I think we'll definitely do this again next year. And I think we met our objectives, and thank you all for joining. I think that's it. So yeah. Yeah, Martin, if you want to say something, or yeah. yeah. I think.
Yeah, no, I was just going to reiterate my thanks for you putting it all together, and hopefully I'll see you in a few months' time.
Speaking of which, I was going to ask you that you were still thinking about coming for the symposia, the AAAI Spring Symposium?
Yeah, that's still the case, Mike. That's right.
Okay, I look forward to that. Great.
Yeah.
Thank you guys for joining. We'll see you later.
Thank you.
Okay. See you.